maybe some of you remember that last year we actually did a Kaikago Symposium. This is really a mini informal symposium just to celebrate the papers from UChicago Computer Science Department of the ACM Kai conference. And last year, the situation was a bit more dramatic, but I want to first welcome you everyone before telling you that story. So last year we created this when the pandemic hit because Kai 2020, the conference, the premier conference in human-computer interaction from the ACM, was actually canceled. And our students didn't have a venue to present, besides just pasting their videos on YouTube and things like that. And so we created this Kaikago Symposium, and we had a good time just having a small group of people here and chatting amongst ourselves. And this is also live on YouTube, so people can ask questions through that medium as well. And this year, we're not still going to Kai. Kai would have been in Japan. We could have been hanging out with Shunichi Kasahara in Tokyo and in Yokohama. But unfortunately, we're still not traveling due to the pandemic. But while Kai is happening virtual, there's a number of changes in the format of Kai this year that we decided to also, it would still make sense to still kind of celebrate internally and have this small Kaikago Symposium with our students. One of them is that Kai's talks, because it's this massive virtual conference, are very short this year, only 5 minutes. And today we really want to have, our speakers have more time to present their talks, which we think is really important to also just enjoy talking about the work. And so we have a couple of sessions for you today. The day is structured in 3 sessions. I really hope all of you can sort of just be on the Zoom and attend all the sessions, whether you're asking questions actively or just kind of passively listening. Feel free to also share both the Zoom link with other colleagues and friends that you might think they're interested, or even the YouTube link, and they can just watch over YouTube without having to log into Zoom. Information is also on this Kaikago-remote.eventbrite if people want to check out more information. So we're going to have 3 sessions, as I was saying. The first one is on haptics. My student Jasmine is going to moderate the session. So I won't introduce the speakers yet, just give you a short preview. You can look at my slide. But we have 4 talks on haptics. Then we have a session on privacy and remote learning, and with 2 talks, and then we wrap it up with a session that sort of merges both new types of haptic interaction techniques, but also new ways to visualize information. And I think all of these projects somewhat have an emphasis on visualization. So I hope you'll enjoy these ones. All right, I'll pass it on to Jasmine to moderate the very first session on haptics.
Awesome. Thanks, Pedro. Hi, I'm Jasmine. I'm a second-year PhD student as part of the University of Chicago's computer science program. I'll be kicking off our haptics session. And before I introduce speakers, I just want to give a reminder that if you have any questions, feel free to drop them on Zoom chat or on the YouTube chat. We'll monitor both and try to get to as many as possible. But yeah, otherwise, I'll go ahead and introduce our first speaker. So our first speaker is Akifumi Takahashi, and they will be talking about their paper, Increasing Electrical Muscle Stimulation's Dexterity by Means of Back-of-the-Hand Actuation. So without further ado, go ahead, Akifumi.
Okay, thank you for introduction. Sure. Okay. So, so hi, my name is Akifumi Takahashi, and I'm presenting a work I did together with my Pedro Lopez. And so let me first talk about the background. So the field of the haptics has come a long way in the last decade. So we explore haptics for touching objects in virtual reality and learning new physical tasks and much more. And here we see an exoskeleton glove that can move the user's hand and the finger involuntarily using the motor. But unfortunately, it uses the large motors, and thus not trivial to miniaturize. So these devices are very limited in their application to wearable or everyday situations. And in order to build more mobile applications, the researchers in HCI in the past decades
have been explored a technique called electrical muscle stimulation, or EMS for short. And you can see here how it's very small, because just only the electrodes is put on the forearm or the body. And now using EMS, the people have been building all sorts of interactive systems like this. This system, the possessed hand, maybe it's popular. Many people know, but this stimulate the fingers to press some simple note combination on this string. Maybe it's a little bit small picture, but there is a small string instrument, and then this user is played the instrument by an EMS system. And this system affords by the Pedro Lopez, and it can make you learn how to manipulate an object that you haven't never seen before. And in this picture, the user now learn they should shake a spray can first of all when you use that. And this one called muscle plotter. This is also by the Pedro Lopez, and it controls your wrist and plots a picture using a pen and paper by EMS. And this one can move your wrist to tap a beat, so you can learn some beat patterns. And but when you zoom in and seeing what exactly the quality of the actuation provided by this system is, like you see all these systems or many other found in the HC community actuate only large muscles like legs or arm or wrist joint with very coarse movement, like wrist up and down. And in fact, the possessed hand, which is proposed about 10 years ago, is still the most precise system we got. Actually, there is a little bit more improvement, but they also have the problem that I will mention following. And what is preventing the EMS from getting better? So here I'm going to move the index finger using EMS, but so the first joint, which is called MCP, here. MCP is bend, it's targeted to bend, but also the PIP is the second joint, is also moved with the EMS. And also the pinky finger is also bended, even though I just targeted the index finger. So the actuating by placing electrodes on the forearm to control the finger muscles suffers from the lack of dexterity, such lack of dexterity. And why this happened? And then that's because as you can see, all the fingers muscles is densely packed here. And all the finger muscles densely packed here, so it is difficult to selectively stimulate only one muscle of the targeted finger, and the stimulation is propagated to the adjacent muscle of the another finger. So that is the reason why EMS tends to be imprecise when you apply like that. So our approach is to move the electrodes on the back of the hand like this, here. And then we can precisely target the first joint of the finger that moving the others. So now to validate this, we ran a study comparing it to the standard approach, which is just putting the electrodes on the base of the hand. So I compared the back of the hand and the standard approach that is putting the electrodes on the forearm. And we found that our approach is flexed more independently, like this, or it's not like this. Yeah, our approach is just only flex only the index finger, other than standard approach. And also here we can see that this is the independent index that is calculated. First of all, I calculate the angle of the fingers while applying the EMS, and then calculate the independence index, which is how the EMS can flex the finger independently. So our approach, the blue box, is much higher than standard EMS, that is the orange box. And then this is generally can be seen like this. So our approach flexes more independently. And the second, our approach has less unwanted movement. That means that so the standard approach also makes the flexion of the PIP of that joint, but our approach does not make the flexion of the PIP. So this is the ratio of the PIP to MCP, of the angles, and our approach is more or less fraction of the PIP ratio like this. It is also generally be seen like this. And also, our approach is more invariant to the rotation. So it's really first. So here, the standard approach is calibrated carefully to make the only ring finger, maybe middle finger, yeah, it's ring finger flexion, only ring finger flexion by this posture. But when rotate arm, it also middle finger and the ring finger, the two fingers, is flexed. So in this case, the standard EMS is that means the standard EMS can be easily messed by the moving the arm. And while our approach is our approach is invariant. Yeah, our approach is invariant, like to the rotation, like the only ring finger is bended even if the arm is rotated. And then this shows that the most left plot shows the index fingers plots, and then in this case, our approach is not much changed the independence index value, but the standard EMS has generally low medians and medians like this. But some people, the index fingers independence index is much get better when rotate arm. So that means the standard EMS is a very variant. It's variant to the rotation. In other case, the pinky finger is very easy to understand. Our approach is not invariant, but standard EMS can be seen that the standard EMS the calibration is messed like this, and then very independence index of the standard EMS is very got low like this, and generally it's seen like that as such. Though lastly, we know that we found that our approach is very easy to calibrate. So our approach can be calibrated within the 5 minutes like this, but standard EMS has very long time to calibrate. Around the median is 15 minutes. So it's very long time. So using our back of the hand actuation, you can build new application at the new level of dexterity. So let me show you a few applications. Oh, perhaps I have really long. And in this case, the finger is presses all the strings at the one fret. In this case, the ring finger pull the sticks to the tap beat. It is not can be realized by the standard EMS. And also, there is the piano application, and this is not realized by the standard EMS because it has low independent flexion of each fingers. So actually, and in fact, I can show you piano demo live, but sorry, I too much talk. So can I have? Do you have the time to show the live demo? Okay. So. So let me stop the share, and I'll share everyone. And I'll share the link to the my web app, and where you can control my EMS like this, and you can control my hand by EMS by the web app. There's OBS, and here. Someone.
All right.
Someone now logging. Oh, Brian has got it started. Oh, so Brian, could you press the colored finger button and hold? So maybe my finger is bent.
Okay, 1 second. Make my window so I can see you. All right, great. Let's do index finger.
Oh,
yeah, there we go.
It's coming. Can you?
And then the ring finger. There we go. Maybe do your middle finger. And then your pinky. All right, my turn ends in 6 seconds.
Yeah. Oh.
Play quick melody.
Nope, too late. Someone else has it.
So could you someone again log in and either? Oh, so could you press and hold the button to control my finger via EMS?
Sorry, I'm trying to press got it. It's the top one, the color key. So I was wondering,
So very short stimulation cannot make the enough friction. So please a little bit longer.
So I was wondering, can you actually press both keys? I guess in this demo, probably not, but in real life, can you press both? What happens if you press both?
Actually, in this demo, I haven't implemented the both key, but actually it is possible to make the system in the future.
Okay, sounds good.
Yeah.
Very nice. Thank you very much.
Yeah, thank you very much. So, so if someone else wanna try, please enter your name and the press button. Or how long I have the time to for my turn in this talk?
Okay, so I'll give it a try.
Yeah.
Hi, this is an awesome demo, by the way.
Yeah. Oh, yeah, come in.
So how much is the lag like in when I were to press the button like right there next to you? Because I'm like transferring the signal from my laptop to your system, right? So there must be some lag over there, but what's like the real time lag?
I actually don't measure the lag time, but
okay.
Yeah, so yeah, I don't know, sure.
It seems pretty short over here. Like I'm pressing down on the button and yeah. Super cool, super cool.
Yeah, thank you very much.
Okay, in the interest of time, we might want to wrap up. And then we also have some questions in the chats that we can get to.
Sure.
Aki, do you have other slides or are you ending with the demo?
Yeah, so okay, I have the last slide. Yep. And then, yeah. So now, so thank you for trying my demo. And now backward hand is actually not without a limitation. So I'll talk about the limitation. As I mentioned, you can only move the first joint. And then, so there is still a lot of way to go for us to unleash the full dexterity of EMS. I mean, we need to move the second joint or the third joint. So I have to unleash these joint movements for the full dexterity. And also, we have to unleash the extending. And then that's extending, the extending is can be realized by the stimulating on the forearm, on the forearm. So we have to make a combination of the back of the hand, also forearm, for the full dexterity actually. Yeah, so that's all. So I'm really excited to see what all will build with the back of the hand. So so thank you very much. That's all.
Thank you, Aki. Also just wanted to note that this received a Best Paper Award at CHI, so really amazing work. We have one question from YouTube from Sophie Tosas. Very cool work. Have you used this for the thumb?
The
thumb.
Thumb?
Yeah.
Yeah, actually, on the back of the hand simulation, I couldn't make the thumb actuation. Actually, I can make the clothes movement, but it's not like this movement. So actually the thumb joint is very special joint. It has a very high freedom of degree of freedom. So it's very difficult to make the good flexion. So yeah, so I couldn't make that for now. Yeah, thank you for this question.
I don't see any other questions, but if anybody has them, feel free to jump in. We'll maybe do one more before moving on to the next talk. Okay, I'm going to take that as no questions, but feel free to drop them in the chat. I'm sure Aki is happy to answer them if anything comes up. Okay, so next we have our presenter Kongpyung Moon, who is presenting the paper Elevate a Walkable Pin Array for Large Shape-Changing Terrains. So feel free, Kongpyung, if you want to start sharing your screen. Awesome.
Okay. Hi, everyone. My name is Kongpyung Moon from Mac Interact Lab at KAIST. Thank you for joining our presentation. And it's a pleasure to present our project, which has been collaborated with Human-Computer Integration Lab at the University of Chicago. This paper was a teamwork with great researchers Sung Jae, Hanseung Shan-Yuan Teng, Jess Brooks, Professor Pedro Lopez, and Professor Andrea Bianchi. Unfortunately, our first author, Sung, is unable to present today due to his military service. So I'll be presenting today on the Elevate a Walkable Pin Array for Large Shape-Changing Terrains. So today, the HMDs provide endless possible spaces to explore, like even the places that we have never visited before. So in VR spaces, you could actually walk around the room, climb the stairs, or even go to a rocky mountain. However, this causes a dramatic gap between like what you see and what you feel. So, and we believe people should not only be able to walk around, but they should be able to feel beneath their feet. So when we look at precedent studies, like researchers have developed wearable devices that deliver foot haptic feedback to the user's feet. Gilded Gate utilizes vibrotactile feedback to simulate the perception of different ground textures to the users. And Real Walk creates a realistic sensation through MR fluid actuators of the ground surfaces. And the Level Up allows users to experience walking up and down through the mechanism that is attached below to the booth. Yet this instrumentation causes a discomfort to the users while they're experiencing in the VR environment. So we look at pin-based shape-changing displays where you could render different topologies very freely. For instance, Pocopo, Inform, and Shapeshift, which are one of the major examples of them, are handheld devices and tabletop shape-changing pin arrays that renders 2.5D objects for VR experiences and provide dynamic physical affordance as well. However, the limiting factor is that they require individual actuator for each pins, and every linear actuators cannot withstand human weights. So we could not really stand on it. But while there are shape-changing floors, such as lip tiles and tile puffs that users could actually walk on it, these platforms are limited to low resolution, and inflated actuators are not stable enough for users to stand and walk on it while it's lifted up. And as you see on the right side, there is a ALF, which is an abbreviation of a live flow, where you could actually stand and walk around while it's moving, but they're not quite capable of generating high resolution terrain due to its limited number of actuators and its triangulation of the surface, being unable to provide feeling of standing on textures and uneven ground. So in order to provide a platform where users could stand, walk, and feel different terrain topologies with their feet, we propose Elevate, which is large enough to walk, solid enough to stand, and has sufficient resolution to render a variety of physical terrains with a finite number of actuators. The length and width are 1.5 meters by 0.6 meters, which is around 1.1 square centimeter square, This large shape-changing display can generate various high-resolution terrains within minutes. As you can see in the clip, you can stand and walk on it, and you can actually lie down on it as well. And he's our first author of our paper. And it shows that Elevate is large and strong enough to carry human weights. So what can we do with the Elevate? What could be the applications? So we suggest 4 applications for this project. The first application is the landscape. The terrain that users sees in the VR is mapped on the Elevate so that users could walk and feel the terrain that they actually see on the HMD. And it could render different terrain topologies as in VR. The second application is stairs. As you literally climb up the stairs on the Elevate, it gives you a more immersive experience as you navigate inside VR spaces. And Elevate could generate various types of stairs by adjusting height of the pins. The third application is stepping stone. In this application, users could experience the dynamic changes of the terrain through VR interaction. So you could throw the stone with the Vive controller, and when the stone falls down the cliff and it rises up, and it changes its texture, telling it's ready to step on. As you see in the previous clip, it does take some time to generate the full terrain, but this can be compensated through the interaction in VR environment. And the last application is mini golf. This shows that Elevate, although designed to enhance the real walk experience in VR, it could be utilized for other applications such as mini golf, where you can play golf on dynamic terrain. So we made a golf terrain web application. You could change the height of the pins and create bespoke golf terrain. Once you finalize the design and save it, Elevate immediately updates the terrain, and you could set up dynamic obstacles, which are hard to find in actual golf field. So how does all this thing works? So first of all, how does this application and hardware communicates with each other? And to do this, we developed the communication firmware where you just need to input pin array map that contains the height of each pins. And once you have this map, the communication firmware tells the hardware what to do. For instance, when and how much to move horizontally, when to unlock the pins, when to push, pull down the pins, and when to lock it back again. So when it comes to hardware, it consists of 3 parts: pin array display, locking system, and shape generator. There are exactly 1,200 pins, 20 by 60 in an array. They are wood pins with 14,400 magnets. So there are 12 magnets for each pin. And the length and the width of the pins are 3 by 3 centimeters, and it has 10 discrete height location with 1.5 centimeters per level. Therefore, Elevate can generate high resolution terrain. The shape generator has 10 actuator modules with 2 DC motors each. So you could push and pull single row at the same time. And the shape generator moves horizontally with 2 stepper motors, and it takes 1.1 second to move to the next row. And this push and pull, large pin array display just with 10 actuator modules, and it takes 10 seconds for a single row to push the pin up to the maximum level and come back to the base. The electromagnet on top of the rack is activated when it needs to pull down the pin. And to make sure the locking system, people can stand on it, we developed our custom locking system. It can lock 80 pins by moving 4 rows of the shaft at the same time. So, oops, sorry for that. Once the pin is elevated, the aluminum shaft moves into the notch of the pin. A single pin without the locking system can only hold up to 6.98 Newton, relying just on the magnets. But once we have the locking system, it could withstand a human weight for every single pin. For the user study, our hypothesis was to see whether Elevate can create a higher sense of realism than the baseline condition, which is no haptic device. And the second hypothesis was to find out whether Elevate is more enjoyable than the baseline condition. For this study, user experienced landscape and stepping stone application as a single coherent VR scene to experience both dynamic and static states of the terrain. And we recruited 8 participants, aged between 23 and 39. And after the study, we asked them to fill out 7-point Likert scale. And we observed statistically significant difference between the baseline and haptic condition for both realism and enjoyment study. So before I wrap up my presentation, I would like to show you some of the initial steps of the prototype and some of the behind the scene of making Elevate. So we started with a single pin control prototype to test the idea. And we designed a custom encoding system and a lifting gearbox. And then we gradually increased the system and increase the number of the pins. We have to glue 12 magnets for each pin manually. We have to make sure that the magnets are perfectly inserted. Otherwise, it was stuck on the grid. And these tiny details were very important to make the entire hardware work. And we have to minimize the friction between the wood pins. So we have to sand all 4 sides of the pins manually. And I remember sanding all day on my first week of my PhD. So that's the end of my presentation. And if you have any questions, please feel free to ask, or you could also contact Sumo as well. Thank you for listening.
Thanks for that talk. The engineering for this is just so crazy impressive. If anybody has questions on Zoom, feel free to jump in. I don't see any questions on the chat, so feel free to just unmute yourself and ask.
I have a question. So it seems that the trend is definitely higher and higher resolution for these kinds of pin displays, especially the large ones. And what do you see as the next technology to make it scale up?
So I think the current limitation of our system is the terrain itself. We could generate the terrain dynamically, but while it's moving, we couldn't really step on it. So the next would be having stepping on it and moving at the same time. So that would be another mechanical challenge, but also that would open up a different application of experiencing a haptic terrain in VR environment.
We have some questions on the Zoom chat. Ray Tsai asks, I'm missing why 12 magnets are needed.
Oh, okay. So there are 10 steps, 10 levels of the height. And we have one extra steel plate at the bottom so that it holds the pin while it's not, even though there is no locking system is on. So there is one extra on the top. So 10 notches should be 11 magnets, but one extra for the metal plate. So it becomes 12 magnets.
We have another question on the Zoom chat asking, do people ever trip on the surface?
There were some participants. We didn't really ask him to trip, but he was actually lying on it and was enjoying the flowers in the VR scene. So it was really interesting to watch people enjoying the experience.
Sounds super fun. Any other questions?
I had a question. With regards to the resolution of how many things you can bring down at the same time, because it looked like you're based on your locking mechanism, you can only bring down you can bring down four of each of the pins in each row. And I was wondering if you could make that more discrete to say maybe bring down the whole thing while a person's standing on it, or maybe have something fall from someone's feet to, I don't know, make the implication that they're maybe on an edge and a stone is dropping.
So for instance, the shape generator can change the height of the pins of a single row at the once. And so if the full row has to bring down, then it can't bring down. But the locking systems are grouped in 4. So there are 12 locking systems of 60 rows. So for if a one row has to change in that same group, then all 4 rows are a bit in a fragile condition, or where it's really relying on the magnets. So that's, I think, the current limitation that our system has it. But the whole point was it's like not massively using actuators for every single function. So we have to make it some trade-offs. But is that an answer to your question?
Yeah, I was just wondering what the constraints were.
That's the current limitation we have at the moment.
Okay, I'm going to ask one more question from the Zoom chat, and then feel free to answer any other questions that you see pop up in the chat as we move on. But Romaine asks, have you ever thought of a way to smooth the surfaces between the pins? I'm thinking it may feel like stepping on Legos.
Yeah, I think that's an interesting question, because the shape of the pin actually influences a lot to the feet when you really step on it. So for our study, we didn't really let people, we let people to use their shoes, like wear their shoes. We didn't let them to try it with the bare feet. However, like there could be some other method to cover on top of the pin with different textures, perhaps different shapes, like patches, and maybe that could give a different sense of ground. But like as we've seen in the related work, having to achieve a smooth surface, we have to triangulate the surface. But the triangulation actually brings a lot of limitation in terms of providing resolution, because once you have a steep triangles, then there is a huge gap between the triangles. And we thought that would be dangerous for people to actually step on it. So I think that was having the current system might be not fully provide very smooth surfaces, but that was a bit of a trade-off that we made.
Awesome. Okay, I see another question, but feel free to answer on the chat. So now we'll move on to our third speaker, Shunichi Kasahara, who will be presenting the paper, Preserving Agency During Electrical Muscle Stimulation Training Speeds Up Reaction Time Directly After Removing EMS. So feel free, Shunichi.
Okay, thank you for introduction, Jasmine. Let me share my screen. Give me a moment. Right, so can you see my screen? Good. Right, so give me a moment. Okay, so thank you for introduction, and I'm happy to join in this great session. Hi, everyone. My name is Shunichi Kasahara from Sony Computer Science Laboratory. And this work is a collaboration work together with Kazuma Takaza from Sony CSL, and Jun Nishida from University of Chicago, and then Kazuhisa Shibata from Riken, Japan, and Shinsuke Shimojo from Haptic, and Professor Fedor Lopez from University of Chicago. All right. So let me start my... So the last time actually this is the next version of last our paper in kind 19. Then last time in kind 19, we showed that actually it is possible to accelerate someone's reaction time toward superhuman speeds by means of electromuscular stimulation. For instance, as you can see in the video, with help of the electromuscular stimulation, user actually can grab the pen, which is originally hard to grab. And then it was surprising that we found in kind 19 is that we can accelerate this reaction time with electromuscular stimulation, but still without fully compromising sense of agency. Sense of agency is a feeling that I am doing that. So let me show how it works. And then imagine that this line is a user's fastest reaction time. And then the vertical line is like the feeling of the sense of agency. That is like how we feel this is my action. Then when we imagine that this line is at the fastest reaction time, of course, so we can if we are using EMS, electromassive stimulation, then we can make the construction of our muscle to go to the pain. But if you apply EMS very naively, that's much faster than you can do. But obviously, we lose sense of agency, which means that we cannot feel that I am doing this. So this, we cannot feel like, oh, this is my action. So the question is like, so the question here is, no matter which point in this region between that's human original reaction time and speed and the completely losing sense of agency. And then if it's faster than our original reaction time, do we lose sense of agency always, or something happened? And then last time in the Kind-19 paper, we show that we actually find this is not binary function, but we found this curve. This is the agency curve that's like even the faster than our reaction time, but still there are the temporal region that we can preserving sense of agency and accelerating since the human's reaction. So which means like we can, for instance, we can pick some time parameter to the timing of the EMS to preserving the sense of agency and still being the faster by means of EMS. Okay, but the last time in the Kind-19 paper, we actually presenting that work in Kai, and we actually get a lot of question about whether this fast reaction time still occur after user remove the device. So this is a very interesting question, because when we imagine that the technology augments human abilities, and what happened if we remove that technology? Do we still get some ability to with human augmentation technology? So this is the main question of this paper. So what happens after you remove the electromassive stimulation device? So then we are really interested in this question. So this year we tackle this question, right? So then this paper is not talking about what happened during the EMS, massive stimulation, but after you remove the massive stimulation device. So is there any effect of EMS training that you make faster even after removing EMS? So we investigate this question with a simple visual reaction time. Sorry about that. This is not a video. So as you can see in this graphics, the participant saw the LED flash and then asked to tap as soon as possible with their ring finger. And we measure the reaction time and then compare how reaction time will change after EMS training. And then EMS training sessions, the EMS will actuate our ring finger with various, afterwards, I will talk about it later, but various conditions, right? Then, so to investigate what will impact the task and faster reaction or motor adaptation to be faster in reaction, a simple reaction time task, we designed 3 different conditions of the EMS training. So as you can see, this is a simple diagram of the visual reaction time task. You can see when you see the LED on, then participant asked to tap. But we designed 3 different timing of EMS training. Then the first one is a fast EMS. This is a EMS was applied as fast as possible. It's a kind of completely same time with the EMS, LEDs on, which makes like a super fast than we can do usually. But obviously this is not, we expect no sense of agency. And then agency EMS is what we want to really investigate, because when we think about the agency curve, what we showed before, this the horizontal line is the reaction time, and then vertical line, the sense of agency. And then you see the timing of, if the timing of EMS is much faster, super faster, we lose the sense of agency. And then when we design the kind of intermediate timing of the EMS, of course, we can provide the faster reaction time, but still sense of agency is preserved. And also as a counterbalance of the baseline condition, we also designed the late EMS condition, which is actually the EMS will not contribute the touch because the EMS EMS is applied after the human's touch. Right. Then this is the EMS training sessions. Then we compare the pre and post. So let me show. Sorry, I forgot the animations. But anyway, so then our main, as a reminder, what we are interested in is not during the EMS, but most important things are pre and post. Then how the reaction time is the changes. So we designed the studies like a pre-reaction time measurement in the study trials, and then EMS training. And then after that, we also measure the post-trial without EMS. Then we compare the pre and post reaction time without EMS. Okay. As a reminder, to avoid some of the contamination of the EMS effect, we designed the different day the studies design. So we designed the counterbalance, the fast EMS, the agency EMS, the late EMS condition in different days to avoid some of the contamination of the EMS, the mode adaptation effect. Right. So here is what we found remarkable. We found that only when we trained with agency preserving EMS, we found the speed up even after the removing EMS. So as a reminder, agency preserving EMS is actually slower than the faster EMS training, but still your reaction time gets faster without EMS. So this shows that the preserving agency will be the critical factor to train your reaction time. And so the EMS device should be, also the implication of this result is that when we designing the EMS training system, the EMS, we should design that system with the agency preserving way. So why we think this is really important thing, we can apply this finding into the number of applications. For instance, if you are practicing the sports which is heavily rely on the reaction time, then you can imagine that the system that helps you makes fast speed up. For instance, like a 100-meter track dash and preemptively stimulating the right moment, providing the fast reaction. And even after removing the EMS, but still, you will be the faster after the removing EMS. And also, when we think of the more interesting interactive application scenarios, we can imagine that we can apply a power-up item in the video game, which is you can speed up reaction time with EMS, but even also after applying EMS, your reaction time gets faster. So it's actually even after the augmentation of the EMS, but still your ability gets faster. Right. So the things we are very excited about is to be the EMS training, that just only the faster is not the answer, but faster and preserving agency is the answer, is a conclusion. But also we found very interesting because when we think about augmentation technology, so maybe if we can provide like a agency preserving way of the human augmentation, this research provides like a possibility of even after removing EMS, even after removing augmentation, but the effects can be preserved, and then it means like we can enhance human ability even after removing the technologies, right? Sorry. Okay, so then still we have still the open question for the future questions for future researches, because in this time we applied a very simple reaction time, but we didn't include like a decision making the scenarios, and also many other questions about the longer adaptation. What will happen? The EMS speeding up effect will last in day or week or something. And also, the more important question is, in this agency, speed up effect is a correlation or the cause and effect. So that is a very important neuroscientific question, because this agency is actually drives learning, or agency and the learning or the adaptation is just correlation or not. That's a very important question. So we will also investigate those things in the future researches. Right. So thank you for your attention, and then happy to take any questions.
Thanks for the talk, Shunichi. We have one question on Zoom. Zoe, I don't know if you want to ask it yourself. I can also read it.
Yeah. Let me change. Let me find the questions. Reflection time. A different task. For instance, like a typing task. A good professor. I find the questions. So after typing, do people get faster in video games?
So
yeah,
Zoe is asking. Have you tested the reaction time for different tasks, such as after doing the tapping task? Do people get faster at like pushing buttons on video games?
Yeah, unfortunately, we didn't test the generalization of the adaptation, because we tried this effect in the completely same setup of the devices. But we believe that because our setup is very simple and also the can be generalized. So even we didn't test it like a generalization of the setup, if the motor the action itself is the same as the training, we believe that that's gonna be the generalized. But we didn't expect this faster reaction time will generalize to another body move parts. This is still open question.
If anybody else has questions, feel free to jump in, unmute yourself. All right, if there are no other questions, if things pop up in the chat, Shunichi, feel free to answer them directly on Zoom. Otherwise, we can move on to our last talk of the session. And also just wanted to say a note to thank all our speakers who are speaking from Japan and Korea, since I know it's like really late at night. So we really appreciate everybody joining us for this session. All right, okay. Now, for our last talk, we have Shan-Yuan Teng presenting Touch&Fold, a foldable haptic actuator for rendering touch in mixed reality. All right.
Hi. My name is Shan-Yuan Teng, and today I'm going to talk about our work, Touch&Fold, a foldable haptic actuator for rendering touch in mixed reality. And this is in collaboration with my colleagues Pengu, Roman, who is also here, Joshua, and my advisor, Pedro Lopez at the University of Chicago. We engineered a foldable nail-mounted haptic device for mixed reality. Here, the user follows a guide to repair the bicycle. this is a virtual interface they see. And when they touch this button, our haptic device unfolds a cover that pushes against the user's finger pad to create a sense of touch. Then it tucks away, leaving the finger pad free. The guide then instructs the user to use a screwdriver to unscrew the brake pad. Because our device folded away from the finger pad, it allows the user to manipulate tools without impairing haptic sensations. Why did we build this? Mixed reality allows overlaying digital contents with the real world. However, in terms of haptic feedback, it's quite different from virtual reality. That is because there are not only virtual interfaces, but also existing physical objects throughout the interaction. Previous works for force feedback in VR, including a glove with exoskeletons, braking mechanisms, or using pneumatic jamming. To allow less abstraction of the hand, as in mixed reality, my advisor et al. Have explored an approach utilizing electrical muscle stimulation that can provide force sensation without obstructing the hand. But it can only provide force feedback, not the sense of touch. For tactile feedback, previous works includes a glove with vibration motors, screen stretch mechanisms, and motor and pulley. However, this decreases dexterity and blocks haptic sensation from the real world, and they are not suitable for MR. To minimize the interference with the real world, film-based haptic interfaces leverage electrotactile and fluidics. However, as previous studies have shown, thin films can still impact feeling textured surfaces. That is because our finger pad is very sensitive. So here we ask, is there a way to keep users' finger pad free, yet to provide realistic haptic touch feedback? Our approach is to touch and fold. When the user touches a virtual bicycle wearing our device pushes against the finger pad to render the sensation of contact. When the finger leaves the virtual tire, our device falls back onto the nail, so that the user can touch and feel the texture of the real tire. Let me show you how we engineered this. The device consists of clear 3D printed shell, rack and pinion, a DC motor, our custom PCB containing an NRF microcontroller that some of you from the class may be familiar with, and Bluetooth antenna and a battery. The cover slides and rotates through the hinge and brings down a vibration actuator to touch the finger pad. This is how we create a sense of touch. Let me explain the mechanism in a slow motion video. First, the pinion unfolds the cover when the cover passes its hinge. It folds inward. Finally, it is pushed flush against the finger pad. The pinion then rewinds the cover when the interaction is finished. Our device provides fast contact, and we measure the average force being 0.34 Newton. We also measured the contact area by ink contact test with an artificial finger and confirmed that the vibration motor can fully touch the finger pad. We will open source our files, including 3D printing models, schematics on our lab website soon. A wide range of haptic sensation can be rendered with our device. Our device renders a sense of contact for a virtual surface. The cover unfolds and applies pressure onto the finger pad. Our device can render variable forces. For example, a button feels different pressure when pressing down. The cover stops when touch is sensed by a force sensor, creating a light force. Then the motor applies with more pressure. Our device can render textures as well. For rough textures, like a corrugated cardboard, our device rocks the cover back and forth on the finger pad. For fine textures, like a piece of sandpaper, our device brings down a vibration motor that vibrates on the finger pad. We conducted a user study comparing with the prior work by Endo et al., which is putting a vibration motor on the nail, and that is the only existing haptic approach that also leaves finger pad free. We tested several virtual objects in MR environment, including the contact of surfaces such as a concrete slab, a piece of cloth, and pressing of a force changing button, and textured surfaces such as a piece of corrugated cardboard and a sandpaper. The participants feel that our foldable actuator provided more realistic haptic experiences for the objects except for soft surfaces, because some participants felt the feedback to be too strong. In another study, we wanted to understand the user experience of using our foldable actuator when they are engaged in a task involved both real-world objects and virtual interfaces. We designed a bike brake repairing MR instructions. In this experience, the participants wearing our device would feel virtual buttons while they go through these MR instructions and be instructed to feel textured surface, including the brake pad, which contains small scratches, and feel the oily part on the brake, and to use handheld tools, including a screwdriver and a lubricant bottle, and finally manipulating a small physical object, which is to screw a nut. And we found from observation and participants' feedback that our device preserved the dexterity to perform these tasks and the haptic perception in this MR experience. Let me show you some more applications. Here, we demonstrated an on-body interface. The user wearing our device can feel their skin directly when they tap on their arm, and they can also feel the contact when the interface expanded and mid-air interface to display their physiological data, for example. We also implemented an MR furniture editor where the user can transit between feeling their real table and also the contact of the table's virtual extension using the vibration on our device. By wearing two of our foldable haptic actuators, we showed that the user can grasp a physical knob on the stove as our device by default leave their finger pads free. But when they turn the virtual timer knob, they can feel the contact and vibration detents generated by our two devices. Finally, we integrated our system into HoloLens mixed reality toolkits. The user can feel feedback from virtual piano keys and from keys on the physical keyboard. When the user pinches the slider, both the devices unfold and touch finger pads, creating a sensation of something in between. For future work, more existing haptic actuators can be integrated into our device. For example, Peltier elements can be put onto the cover in MR, and then the user can feel the contact of a hot coffee cup and feel the heat as well. So this is Touch&Fold. It is a system that highlights the importance of designing haptics with finger pads free to feel the real world. Lots of prior haptic devices only work in virtual reality. We were excited to explore solutions that work in the virtual and the real world as well. So we don't have to choose sides and can enjoy haptics in whichever world we are. Thank you very much. And we invite you to come see our demo at the upcoming KAI.
Thank you, Shan-Yuan. Also, just wanted to note that this paper received an honorable mention, so very excited to see it out there and presented here. Okay, we have one question on Zoom chat. Ray, I want to also give you the opportunity to ask and unmute yourself, but if not, I can also just ask it.
Let me check on the chat.
Okay, I'll go ahead and read it out. So Ray Tsai asks, I'm curious about, do you use any encoder in this device or only use a pressure sensor as feedback to the motor control? And yeah, you can read it as well.
Accidentally unshare my screen. Let me just share again.
Okay.
Yeah, for the cover to touch the finger pad, currently we use a force sensor as a way to control the force. And for the unfolding parts, we also place a photo interrupter, which can cut off the DC motor when it's unfolded. Let's share here. So that's how we control the motor now. And for future work, we also consider using more fine-grained encoders so that more force profile can be designed and applied to the user's finger pad.
I think we didn't see your screen, Shan-Yuan, if you want to share again.
Yes, so the force sensor is actually in between the cover and in between the cover and the finger pad, which is very not easy to see here. Let me stop here. So there's a vibration motor, and in between this vibration motor and the finger pad, there's a force sensor, which to sense the force applied to the finger pad. And here, the black is a photo interrupter that is used when this whole thing unfolds and to stop the motor. Hope that answers your question.
Okay, we have another question from YouTube from Sophie Tosas. She has two questions. In your study, it seems like the soft stuff did not work well, but everything else did. Any ideas on what could be needed for that? And then her second question is also, what's the most complex task you could imagine someone doing while still wearing your device? Stove application is cool. Could somebody cook with this? It would be super useful to see recipes in AR.
Thanks for the questions. So for the first one, that's actually that's just something like as follow up from the encoder problem, because for the software, the participants feel the feedback to be too strong than they would expect for a cloth to touch them, and that was because while our force sensor can sense the force feedback, but because the speed was pretty constant while tapping on the finger pad, and it creates a much stronger force than people expected. And we envision in the future we can use more fine-grained encoder to slow down the cover movement so that I can create a slight force on the finger pad. And for the second question, that was very interesting one. And currently, we in our study we try to involve as many of complex scenarios as we can think of, such as filling with multiple different materials in this sense. And obviously, in the real world, there are more complex scenarios, such as there can be, you might want to like wash your hand, but for now our device is now waterproof, and you might want to touch some, you might touch other things with our devices that can be too hot, that our devices is not really hot resistance from now, such as if you touch a hot pot. So there are many things to be considered while interacting with the real world objects. And we thought this is a very exciting direction, and we hope more works can focus on this part. That's my answer. Thank you.
Okay, we have another question from Heather. Don't know if Heather, you want to unmute yourself to ask?
Oh, sorry. Yeah, so that was interesting work. I'm just curious that since you want to not separating the virtual and physical world, which is very cool. So if you blindfold the user, can they tell whether you're actually from virtual or touching the virtual or the physical objects? That would be awesome.
Oh wow, that's let me think. Actually, that reminds me of some pilot study that I did with my advisor one time in our lab. That Pedro was wearing my device to touch something to test our study, and then I also put another 3D printed cube on the table, and for some times Pedro wasn't sure about if he was touching the real one or the virtual one. But that was a very simple example. It's just a white cube. But I thought this is a very cool thing that to explore, like how complex things can be tricked to the user that they're feeling they're touching a real stuff.
Very cool work. Thank you.
We also have a question from Ken in the chat. Also want to give the opportunity for you to unmute yourself.
Here. I was wondering how you can work with the limitation of kinetic feedback, where your finger can still pass through, the virtual boundary. And I guess, after sending that question, I thought maybe EMS can help, combine with together. But yeah, I just want to hear your thought.
Yeah. Currently, our device only provides a sense of touch, so the user will still pass through every virtual object, which is not natural. And to create something that can resist the finger movement, EMS can be a potential solution. And we also thought about using a symmetric vibration, which can create a pseudo force. So the user might feel not the real force, but the tendency to want to pull back their finger. And that can be kind of more naturally integrated in our device because we already have a vibration motor.
That makes a lot of sense. Thank you so much.
Thank you.
Awesome. So I think that's all our questions. And we're also closing in on time. As a reminder, we have another session at 10:30 on security and privacy. So please feel free to stick around for that. But also just wanted to give a last thank you to all our speakers. This was a great session and really enjoyed hearing everybody's talks and all the Q&A, great questions. So yeah.
Awesome. Make sure to stick around. I'm just going to share my screen so everybody can see a preview of what's coming.
Brennan. I'll be the session chair for the next hour-ish. I'm a first-year student in the computer science program, and I'm excited to be sharing in this event with you all. For this session, we have 2 papers being presented. They're fairly different yet related in the broader field of privacy and security. Roughly plan to have Maia go first for the 12-minute presentation, followed by a Q&A, and then Chen will follow with Zulin as well, actually presenting another 12 minutes, again, followed by a Q&A. I think we'll have plenty of time for presentations and some great questions. So let's get started. First, we have Maia, who will be presenting a paper entitled Understanding the Security and Privacy Advice Given to Black Lives Matter Protesters. An inspiring work where the authors analyzed online protest guidelines and surveyed BLM protesters for the degree in which they understood, heard of, and followed these guidelines. This paper received an honorable mention at CHI, so that's impressive as well. Maia is an undergraduate student here at UChicago in the supergroup, working with professors Blaze and Marshani. Fun fact about Maia is that our presenter is that Maia plays the alto saxophone. That's cool. Anyways, the proverbial stage is yours, Maia. You can unmute yourself.
Thank you, Brennan, for that great introduction. As you said, I'm Maia, and today I'll be giving a talk on our project. Black Lives Matter is a global activist movement that aims to address violence against Black communities. The hashtag Black Lives Matter movement, or BLM for short, began on social media as a response to the acquittal of George Zimmerman for the murder of Trayvon Martin in 2013. The BLM movement has since grown into the organization it is today. It consists of over 40 registered chapters across the world, but the BLM movement as a whole remains largely decentralized. It relies heavily on social media to connect chapters and supporters of the movement together. During spring and summer 2020, the BLM movement had an influx of support online and offline. The murders of George Floyd, Breonna Taylor, and Ahmaud Arbery sparked one of the largest protests in U.S. history, involving more than 15 million people, many of whom were protesting for the first time. Many BLM supporters attending these protests had a multitude of concerns, including about computer security and digital safety. Our main goal in this project was to characterize the security and privacy advice given to these novice protesters, as well as their understanding or use of that advice. We were particularly interested in advice given to protesters about security, surveillance, and privacy relating to their participation in the Black Lives Matter activities and protests. In spring and summer 2020, many news organizations and BLM supporters started distributing safety guides, or succinct sets of advice on how to stay safe at protests. Many of these guides included physical safety advice, but some also mentioned advice relating to security and privacy. To understand the advice given to BLM protesters, particularly novice protesters, we collected safety guides from Google and Twitter, using keywords like Black Lives Matter Protest Safety Guide or BLM Protest Security Advice. We collected 91 safety guides in total. 3 guides came up in both our Twitter and Google searches, leaving 88 unique guides. 41 of these safety guides mention digital privacy and security. We then systematically analyzed and clustered the security and privacy advice found in these safety guides. We found 13 classes of advice, including advice aimed to protect against phone confiscation, like using a strong passcode, advice aimed to protect messages in web browsing, like using end-to-end encrypted apps like Signal, advice about disabling phone communication features, like turning on airplane mode, and advice aimed to protect protesters from identification, like using caution on social media. Appearing in 31 guides, disabling transmissions from phones was the most prevalent piece of advice in the safety guides. Of the 31 guides, 18 mentioned using airplane mode, and 8 recommended their protesters turn off their phones. Additionally, guides also recommended turning off location services, Wi-Fi, Bluetooth, and cellular data. All of these features went on transmit data that can be intercepted by law enforcement. Also, many guides recommended that protesters not bring their primary phone to a protest at all. 19 guides mentioned leaving phones at home, while 16 mentioned bringing a burner phone. Many of the guides did not offer an explanation for this advice. The ones that did were vague and did not detail to protesters how following this advice can prevent police from tracking them and protect the data on their phone. 28 out of 41 guides mentioned turning off biometrics, and 11 of those guides mentioned using a passcode instead. However, only 6 guides explained why following this advice is important. Some guides explain that biometric makes it easier for other people to access your phone, while others use vague statements such as, it might be best to deactivate facial recognition or fingerprint unlocking if you're concerned about being approached by the police. Only 2 guides mention specifically that biometric disclosure can be compelled or coerced, the key rationale for this advice. Using a strong passcode was also mentioned by 20 guides, and 12 of those guides mentioned using a passcode or password instead of biometrics. Unfortunately, only 7 guides explained the purpose of this advice. Explanations included protecting data on phones and that passwords are protected by the Fifth Amendment. 27 out of 41 guides mentioned using instant encryption, such as the Signal app, instead of texting. Of those 27 guides, 26 specifically recommended using Signal. 3 each recommended WhatsApp and Wire, 2 recommended Wicker, and 1 each recommended Dust, Keybase, and Telegram. While most guides did articulate a rationale for this advice, most of the reasoning was vague. The most common approach was to simply state that doing so is secure. This does not accurately articulate to protesters the benefit of using instant encryption and how it can keep their messages safe. Numerous guides mentioned advice relating to information and phone sharing. 21 guides recommended protesters avoid potentially identifying information in phones and photos and recordings shared at protests. 20 of those guides specifically are mentioned to avoid people. 14 guides each to avoid faces and people's identifying features, and 6 guides to avoid location. Many of these guides provided detailed instructions on how to follow this advice, such as remove metadata from photos or videos, and blur potentially identifying features. Also, 18 guides recommended caution when using social media in conjunction with protests. These guides most commonly suggested that when contemplating this advice, protesters should consider the impact of social media posts on their other protesters. A few guides also mentioned more intricate tips. 9 guides suggested protesters encrypt their device or phone, while 6 guides advised protesters to back up their device before attending a protest. Following both of these pieces of advice can help protesters protect the data on their phones. Some guides also mention using a VPN and using a secure browser. Both can prevent law enforcement from accessing protesters' web history and their location. 2 guides each recommended disabling notifications and screen pinning. Both of these pieces of advice may seem unnecessary, but can actually be beneficial for protesters. Disabling notifications stops law enforcement from seeing protester messages or call notifications if their phone is confiscated. This protects their messages and the identity of those who are contacting them. Screen pinning restricts a protester's phone to one app. If their phone is confiscated by law enforcement, then they will not be able to access any other apps or data. To understand BLM protesters' security and privacy concerns, as well as to gauge how the security and privacy advice given in the safety guides we collected aligns with protesters' actual knowledge and actions, we conducted an online survey of 167 BLM protesters. 100% of the respondents supported the BLM movement, and 52% identified as African American. 75% of the respondents were novice protesters that had attended only between 1 and 4 BLM protests. The survey asked respondents about the concerns they have about attending protests, their familiarity with advice found in the safety guides, as well as whether they followed that advice when attending BLM protests. When asking respondents about their knowledge and use of the 13 classes of advice, we presented each class of advice as a succinct statement. For example, for disabling biometrics, we use the statement, disable biometric, face or fingerprint unlocking for your phone. Use a passcode or password instead. For each of the 13 statements, we asked if the respondents had previously seen that advice about attending a protest, if they felt they understood the purpose of that advice, and if they followed that advice when attending protests. We also asked the respondents to explain in free text what they believe to be the purpose of that advice, as well as why they did or did not follow it. Our survey results showed that in general, respondents were more likely to be familiar with and follow security and privacy advice that applies at all times, rather than protest-specific advice. For example, more respondents reported using a strong passcode on their phone than disabling fingerprint or phone face unlocking when attending a protest. However, following both of these pieces of advice is necessary for protesters to keep their device safe. When biometrics are enabled, protesters can be forced to unlock their device because biometrics are not protected by law. Passcodes and passwords are protected by the Fifth Amendment, so law enforcement cannot legally force protesters to unlock their device. Thus, it's important for protesters to disable biometrics and use a strong passcode in order to protect personal information on their device. Using end-to-end encryption is necessary for protesters to protect their messages from third parties like law enforcement. Even though it's therefore especially critical to use an end-to-end encrypted app like Signal instead of texting, respondents were just as likely to report following very specialized, complex advice, like using a VPN or a secure browser like Tor, as they were to report using Signal. Sending messages on Signal rather than text messaging should be much more of a priority for protesters who have limited time for adopting new security practices. Some respondents also did not use end-to-end encryption because they felt that it was too drastic or not necessary for them. One respondent stated, "I'm not in communication with the protest organizers, so my potential benefit to police is little." In short, respondents generally weren't familiar with the benefits of end-to-end encryption, despite it being one of the most common pieces of advice given to protesters. Disabling transmissions on their device and leaving their phone at home are both necessary for protesters to follow and were prevalent in safety guides. However, we found that many respondents did not follow these pieces of advice. 78% of respondents felt that they understood the purpose of disabling transmissions, but only 40% followed this advice. 83% of respondents felt that they understood the purpose of not bringing their phone to a protest, but only 31% followed this advice. When asked why they did not follow this advice, 31 respondents stated that it was unnecessary. Even though disabling transmissions and leaving their phone at home is necessary to protect protesters' location data, not disabling transmissions allows the device to transmit cell signals that can be intercepted by law enforcement and used to trace where protesters have been and where they currently are. Therefore, although it's necessary for protesters to follow these pieces of advice to protect their location data, respondents generally do not follow this advice despite being familiar with it. Moving forward, we are working to build better ways to communicate to novice protesters the key pieces of advice that will help them stay safe at protests. We are now building an app that presents advice to BLM protesters in a more interactive and personal way. We hope that by presenting the advice in this way, we'll be able to show protesters why this advice is important and how they should follow it.
Maia. We will now take some questions. Feel free to raise your hand and ask a question. Also, feel free to drop it in the chat, and we will try to direct them. If on YouTube, you can put your answers or your questions in the chat, and we'll try to put them this way.
Can I jump in there with a question?
Yes, please.
Yeah, that was a really great talk. I'm just curious of one thing. I think these findings seem super important, and I'm even wondering if they're even more important because I was not sure how you all went and selected the participants for the study. So was this selected via a survey? Because I suspect, by the sort of an online survey, right? Because I suspect you already sort of selected a little bit just by virtue of that process for people that are more technologically familiar. And so I'm imagining if you would do this study again and just go to a protest and just, randomly pick protesters, would you even find that exactly the things that you found out, they're maybe not aware of the importance of password versus biometric, that stuff would even, show up more? What's your feeling on that?
Yeah, so when we sent out the survey, we used Prolific and we made sure that all of the respondents were BLM supporters, and some respondents had familiarity with IT or security, but not many. But there is the fact that those that are on Prolific are probably more likely to be more familiar with things like biometrics or using a strong passcode instead than those who are maybe outside just attending protests who maybe are not on Prolific. And so I think that, if we went and we maybe surveyed protesters in person, that we might even find more protesters that are not really understanding these pieces of advice, why they're important and how they should follow them.
That's super cool. Thank you.
I actually have a question as well. So do you have any inclination towards a certain ideal information spreading design in both like the guide design itself and the means in which it's like spread? I mean, I think if I recall correctly in the paper, you touch on how more research should be done on like if it should be infographics or bulleted lists, or maybe that's what this phone app is designed to tackle.
Yeah, that's a great question. So we're currently working on trying to present advice to protesters in a more interactive and kind of clearer way. So right now we're focusing on trying to build an app, and our thought process is trying to see if things like personalization, if we could show protesters that, hey, I managed to pull your messages from your phone because you're just a regular text message, you're not using internet encrypted apps. Would that show protesters, hey, this is important and you need to follow this advice? Or things like, hey, these are stories of protesters who have been to protests, who use their cell phones, they didn't have airplane mode on. And because of that, police were able to intercept their cell signals, they tracked their location, and they were able to arrest them. And so right now we're actually trying to figure out which parts of these presenting this advice in which way is going to actually help protesters understand why it's important. We're probably going to end up doing maybe a focus group, trying to see what people actually deem as something that's motivational for protesters. And we're also looking at ways to present advice maybe in some type of comic format, as you saw on a slide, that maybe makes that advice more interactive for protesters, makes it so it's not just a string of text that they have to read, so that maybe they might be more interested in actually understanding why this is important. So we're hoping that doing things that way will help protesters understand why these pieces of advice are important and how it relates to them and not other people.
That's cool. So like increasing the understanding would then increase just the amount of following.
Yeah, we're hoping that increasing the understanding of why it's important, why it's necessary for them will increase the amount of protesters that are following this advice, so it keeps them safe at protests.
I have another question. This is Heather. Maia, thank you for that's a nice talk, very interesting talk. So I just wondering, when you interview these folks, did you ask them whether they're the first time protester or they're more experienced protester? So once you get a little bit of a context of the protest scenario, would you change your opinion after that?
Yeah, I'm not sure if you mean when we did the survey or you're talking about the future work aspect.
When you do the survey, I guess that's also aligned with the future work is, but I'm saying that my first question is, without reason awareness, even the experience, would that help? And the second related question is, once you raise awareness as a future work, maybe you can also check these. But for the current study, do you have a sense of how many of them are first-time protester or how many of them more experienced protester?
Yeah, definitely. So when we did the survey, we actually asked participants how many protests they had been to, and about 75% of participants had been to 1 to 4 protests. So most of them were novice protesters. And we also noticed them asking participants about pieces of advice or their concerns. A lot of them didn't feel that those pieces of advice were important for them or didn't have those concerns for themselves because they were novice protesters instead of organizers. So we also kind of saw this relationship of organizers tend to really understand these pieces of advice. They tend to understand the importance of it, and they recognize that it's important for them to follow it. But for some reason, novice protesters really don't make that link. They feel that protecting themselves is not important, that no one's looking for them, that the police aren't really interested in them. And so we're trying to get them to understand like these things are important and it is important to follow them. And also, I believe that many of the safety guides were also kind of tailored toward novice protesters as well, because there's this idea that organizers kind of already understand what they're supposed to do. They already like follow these pieces of advice because they've been doing it for a long time. But novice protesters, who there was a lot of last year, didn't really have the same experience. So, yeah.
Thank you. That was great. Thank you.
Thanks, Maia. So is there any way to, I mean, this might be a little out of scope and difficult, but is there any way to gauge the impact of following such procedures, like resulting in maybe like a higher safety of protesters or something? I mean, this would kind of like prove the importance.
I'm not sure what you're asking, Brennan. Can you reword that for me?
I guess. Is there any way to like gauge protesters who follow such procedures versus and compare them like for protesters who like hadn't followed such procedures? Is there like any difference in impact or result?
Oh, I'm not sure. I think that would be an interesting study though to see if those who are following these pieces of advice are actually more protected than those who aren't, if there's like less arrest rates for those who follow this piece of advice. I don't know how you would actually go about doing that, but I think that would be something that's interesting.
Cool. I guess we'll, if anyone has any further questions, give it just a second. Looks like no. So I think we will, if you have questions and you think of any more, we can drop them in the chat and maybe Maia will answer them directly. Otherwise, I think we'll move on to our next presenter. Thank you so much, Maia. That was a great talk. Okay, so the next presentation of the session will be by Yuxin and Zulin, presenting a paper entitled User Authentication via Electrical Muscle Stimulation, where they will explain how we can use the unique physiology of humans for user authentication. These are both PhD students in the SAM lab here at UChicago, working with Professors Ben and Heather and Pedro. So Yuxin and Zulin, if you're ready, take it away.
Thanks for the introduction. My name is Yuxin. Jolene and I would like to introduce Electricals, which uses electrical muscle stimulation or EMS to authenticate users. And this is on behalf of our colleague Ruben and our advisors Pedro, Ben, and Heather. So, all right. Let me show you an example. Here, I put on my VR headset, and it wants to authenticate me using our system. So it sends EMS stimuli to my arm, my fingers move, and it checks my finger movements and then authenticates me. So electric auth is a biometric system, but it differs from today's biometrics. Today's biometrics passively capture our face, iris, or fingerprints. They work, but they are vulnerable to data breach or repair attacks. Once someone records my face or fingerprints, I cannot trust them anymore. Instead, electric auth is an active biometric. It authenticates by sending a challenge to the user and collecting a response. A different challenge will lead to a different response. And to run authentication, the system uses a new challenge each time. So repaying previous responses will fail the authentication. And also, given the complexity of human biology, one cannot predict responses to unseen challenges. Therefore, active biometrics are robust against data breach and repair attacks. And the more challenges the system can generate, the more robust the system is. And in this work, we want to know, can we use our muscles as an active biometric? So this motivates us to consider EMS, which stimulates muscle and generates movements. And our conclusion is that EMS is a great modality for active biometrics because of two key properties. The first one is interceptor reliability. It's a well-known property of EMS, basically because everybody's biology is different, so different users respond differently to the same EMS trigger. And in fact, this has been treated as the biggest disadvantage of EMS. But in this work, we show that we can actually use it for user authentication. For example, in this video, we attach the electrodes to these two persons at the same position and apply the same impulse. As you can see, they respond differently. And the second property is temporal dependency. That is, muscles respond differently depending on their current state. And with this property, we can create a large pool of challenges. So in our system, EMS challenges consist of a sequence of EMS impulses, and we vary the time gaps in between to create different challenges. Here is an example. So we send the first impulse at the same time, but send the second one at different time. As you can see, they respond differently. So Without varying time gaps, we can only create 4K changes using 6 impulses, but with varying time gaps, we can create 68 million changes. And next, Jordan will show a quick demo of our IMU-based prototype. And Jordan just told me that her network connection is not stable, so I will just play a pre-recorded video.
Hi, I'm Zulin, and I'm going to talk about our prototype. It consists of 3 components. The first one is a challenge component. Here you see a EMS device, which is connected to my forearm muscle via these electrodes. And I also have a list of pre-registered challenges here. The second one is a sensing component. I have 5 IMUs attached to my fingers, which will capture my response to the EMS challenge. We show the real-time signal here. The third one is an authentication model, which takes my response as input and will output an authentication result. Later, the result will be shown at this part. So now I'm going to select one challenge and start the authentication. Let's pick challenge 19. So it works. Let's try another one. Works again. Okay. So the final thing I'm going to do is I will turn off the device and mimic the response myself and see if I can bypass the system. So it failed. Okay, that's all. If you would like to know more, please come to our live demo session. Thanks.
So we validated electric OS using 4 types of evaluations. We also considered many types of attacks beyond what Jolene has demoed. And let me show you the key results. So in our user study, we recruited 13 participants. We calibrated EMS to ensure comfortableness. We randomly chose 115 length 6 changes for each participant and collected 10 responses for each change. And with the collected data, we first evaluated electric OS under normal scenario. So for example, here I want to use my arm to authenticate my own VR headset. And the system sends one of my registered challenge and collects my finger's response to authenticate me. And we use false rejection rate, or FRR, as the metric of authentication accuracy. So FRR basically measures the probability that a legitimate response is falsely rejected. And ideally, the measured FRR should match the one configured on the training data set. And here we reported the data, result of planned FRR equals to 5%, and the measured FRR is 5.4%, meaning our system works well on legitimate users. And the second scenario is physical impersonation attack. For example, here I'm trying to log into Jordan's headset using my arm. So the system sends one of Jordan's challenge to my arm and collects a response. And in the user study, impersonation attack has a very low attack success rate, only 0.17% at 5% FR. And the next scenario is record and replay attack, where the attacker directly feeds previous recorded response to motion sensors. For example, here I want to fool Jordan's headset again, but this time I compromise the motion sensors so that I can freely read and inject data to the sensors. And here I have collected a set of Jordan's responses. So when a new challenge coming, I will randomly pick one response in the data set and inject to the sensors. And in our experiment, we found our system is robust against this attack. And the last scenario is real-time synthesis attack. Again, I claim I'm Jordan, and the system sends a new challenge of Jordan. But this time, I use an online synthesizer to synthesize the response. And the idea behind the synthesizer is that it segments the recorded responses into chunks. So when it receives a new challenge, it detects each EMS impulse in the challenge and assembles responses using the segmented chunks on the fly. And we found our system is robust against this attack as well. So next, we conducted a longitudinal study. In this study, we have 2 participants. And the study is 24-day long and under combination of three conditions, including time of the day, humidity, and also muscle fatigue. And we found for both participants, our system is stable over time against different humidity and muscle conditions. And we also conducted technical evaluations. We first measure the runtime inference latency and also the training time of our system. So we ran our system on a MacBook Pro and also a small embedded device, NVIDIA Jetson Nano. And our results show that our system can authenticate a user in 3 milliseconds on laptop CPU and 35 milliseconds on Jetson Nano. And we then trained the authentication model on a laptop CPU and also a server GPU. It took more than 500 seconds and 35 seconds to train a complete model respectively on these two devices. And we also tested using a RGB camera to capture the finger movements and found the accuracy is close to the one when we use IMU. So to conclude, we show that EMS is a new and practical form of active biometrics. It delivers inter-subject reliability to authenticate users and temporal dependency to create many challenges. Thanks for listening. Please visit our website for more information, and also please come to our demo next week to do some live test on Jordan's model. Yeah, that's it.
Great. Thank you so much to the presenters. We now enter the Q&A again. Looks like we have plenty of time for questions. I'll just remind everyone, or for the folks that entered later, feel free to raise your hand, or maybe you can just unmute yourself and ask. Or you could ask in the chat and we'll try to relay them as well, where appropriate.
I have a question.
Okay.
Thank you so much for the talk. I really enjoyed it. And I think this is awesome work. I was kind of curious about like, sort of this is a really great way to authenticate, but can you speak more about the practicalities of it? So for example, does this require everyone to have these, like, are you envisioning some sort of wearable, or what scenarios do you think this kind of authentication would be useful? Because I guess I was wondering about like the cost and whether or not like it fits some scenarios, but not others. So could you speak more about what kinds of ways, or how does it apply, and when do you think it applies?
Yeah, so this is a very good question. So besides the example at the very beginning, where the user already have the electrodes on his body, we also consider two scenarios. The first one is to do accessible authentication. Because EMS is cognitive burden free, so so people with like cognitive disabilities can use this EMS authentication to authentication, and it's very like secure than traditional biometrics. And also many patients with spinal impairments, they already use EMS for recovery, so they can also use EMS authentication with low overhead. And also for some high security sensitive scenarios like opening a vault in a bank, we can actually add the EMS authentication system in addition to existing ones to achieve higher security.
Awesome, great, thanks so much. And I love the slide too, that's super helpful.
Yuxin, looks like we have a question in the chat. Does this authentication, this is from Yuxi, does this authentication could be applied to other body parts beyond the fingers?
Although we just tested on the forearm, but I believe other muscles also have their own like uniqueness across different people. So once we can accurately capture the response on other muscles, I believe we can apply to other body parts. Yeah.
I guess kind of an extension of that, applying it to other body parts is something that could be like built into clothing or something that you're already wearing.
Yeah, that's a very good idea. And we are also like considering to make like a armrest. So have the electrodes on the armrest. So we don't need to attach the electrodes to our like forearm. We can directly put our arm on the armrest to have the.
Oh wow, that's cool.
So there are many other form factors, including the curls you mentioned, also the armrest as well.
Those are potentially super cool. I guess this seems like something that, or at least forearm one, seems like something that Oculus or VR companies would be interested in. Is there like a industry interest, or what's on the pulse for like the industry side of this type of work?
Sorry.
Is there any sort of like industry interest in this, or is there something in like Oculus or VR companies that are pursuing similar types of like work?
Currently, I don't know. Yeah, but maybe probably after when the talk is published, maybe they will have some.
I mean, it seems like something that they would love, I guess. Cool. Do we have any other questions? One. We have a question from Akti. I'm curious if it is possible for the system identify the user when the electrode setup is changed after removing the electrodes and again put them near the position you put before. Is it possible to identify them again?
Yeah, very good question. So we did this in a longitudinal study. Every day we will rewear the electrodes on the two participants. And we found it seems to be stable over time and against the rewearing. And also during the calibration, we also trying to find those positions with low sensitive to the location change. So if for example, if we move the electrodes a little bit and the result will change largely, then we will skip those positions and find other positions.
There's another question in chat. I guess we'll give Zoe a chance to ask it themselves if they prefer.
Thanks for the talk. I really enjoyed it. And I love how you turned the disadvantage of EMS into a great application. So as you might be familiar, we can apply a little bit of EMS to change people's muscle activity without actually actuating their body parts. Do you think that could make the process more ubiquitous? And what would be the challenges to apply that?
Yeah, that's a very interesting idea. I haven't thought about leveraging the EMG before, but I think that's also possible because EMG will also reflect the uniqueness of user's muscle. And yeah, I think this will be a very interesting future work. And yeah, I think that's the answer for now. Yes.
I have another question. Is there like a reason why you use square waves? I guess they're easy, but would be using other waveforms possibly increase like the challenge space?
Yeah, that's also possible. In our current paper, we only consider like a fixed waveform, but we can potentially add more waveform to increase the space as well. Yeah, that's
I guess sorry I cut you off. Is challenge space a limiting factor? Is 68 million a lot? I feel like that's a lot. I'm not sure if that compares to other like cryptographic schemes, but that seems like a lot.
Imagine if you remove you use one challenge every day, and it will be more than enough for whole life.
That's plenty.
Comparing to traditional password, we can actually it's actually smaller than the traditional. If you have the 16 alphabets password, yeah, that will be smaller than that. But remember, we can still increase the length of our challenge. Currently, we only use 6, but if we increase to 16, then that will also increase the trench capacity. But this is a trade-off, like as the authentication time will also be longer than the current one.
Very cool, very cool.
Thanks.
Thank you, Shen. Give it a moment for other questions to come in. All right, I guess we'll probably just take a break then until the next session. We'll start at, I think, 11:30. And that will cover papers in the category of interacting and visualizing in new ways. So until then, I guess maybe just hang tight. Oh, Mark. I thought that was a hand. It was a clap. Thank you. Yes, very. Thank you a lot to our presenters, and I guess hang tight.
Exactly. About 20 minutes, folks. So if you need to like do a super quick lunch break or coffee break, this is your time.
can start our final session now, and thank you everybody for sticking around. It's been a great day so far. So this is our final session. Hi, I'm Brian. I'm a 6th year programming languages student, and I'll be chairing this session. Our session is going to focus on interacting and visualizing in new ways. So it's kind of a mix. We got some programming language-ish papers, and we also got some interaction-ish papers, and this will be a lot of fun. Our first talk is from Josh Brooks, and did you know you can smell in stereo? I did not, but now I do. And he's going to tell us about that.
Sounds good. Let's see. I'm going to assume that everyone can see my screen at this point, so let's go ahead. So hi everyone, as Brian mentioned, my name is Jazz Brooks, and today I'll be presenting my work. Let me just move people's faces out of the way so I can actually see my slides there. I'll be presenting work I did with my colleagues, Shan-Yuan, Jingshuan, Romain, June, and my advisor, Pedro Lopez at the University of Chicago, where we kind of are virtually. So this work is about creating a sense of, well, stereo smell, which might be surprising for some people, by electrically stimulating a special nerve in our body called the trigeminal nerve. So let me start with a pretty simple teaser. So here Shan-Yuan's making breakfast, turns on the stove, puts toast, but you probably noticed at this point, he forgot to ignite the burner. And despite that, he actually finds the gas leak pretty quickly. So how did he do that? He must have had some kind of interface, maybe with smell or something, that helped him. So let me show you what researchers tend to use when they create smell interfaces. Now, most researchers approach smell by, well, producing odors, right? They'll push odor molecules from reservoirs to the user's nose. This is kind of like an analog method using chemicals. And in fact, last Kai presented such a display that used chemical smells from reservoirs to create temperatures. And it's a very standard and sensible approach to smell, but you can see that there's a couple different limitations. Especially, you can see on the left, there's like a large device, and these things are inherently limited by the size of the reservoir, as well as the actuators like pumps and things like that, and what you're actually using to produce the odor. Now, one of the most promising ways to break away from this is to shift from analog to digital actuation, aka electrical stimulation. And let's see, like, how does this work? It's kind of tricky. You have to use these super long prongs that go all the way up until it reaches the olfactory bulb. And you can see arrows here. The olfactory bulb is at the eye level, so they're going to be quite long. And then you have to then go ahead and initiate stimulation, which normally means that you have to have like a doctor or an expert on hand that's going to, one, precisely put those electrodes inside the nose at the olfactory cleft, as well as hold it in place so that the stimulation is consistent. And due to this precision and a lot of like anatomical or stimulation factors that we still don't understand, it doesn't produce reliable smells digitally. So we're kind of exploring a space that's between chemical and electrical stimulation. And we want something that's, at one hand, easy to set up without the need of an expert, right? You don't want to have like a live-in doctor at your house to do things for you. I don't think everyone's going to have access to that. But that also alleviates the messiness and the bulkiness of chemical displays. That's kind of hard to expect people to work with on an everyday basis. Following, we instead approach digital actuation from a new angle by searching for like less invasive locations to apply electrical stimulation, and one that still works for certain smells but without deep implants. So we do this by actually actuating the septum. Let me play this video again. So as anyone inhales, he feels a tingle in his left nostril, which our device renders via electrical trigeminal stimulation. So our device essentially gives him a sense of stereo smell, which it determines by pairing with external gas sensors. So you can pair this with any kind of device that'll provide those kinds of readings, like in this case, natural gas levels, for example. So that's how he actually found the gas leak super quickly, because there aren't that many like parts per million of natural gas in the air currently. But how does this feel, right? Does this actually feel like smell? And it's kind of a weird situation where it's not quite, but actually yes at the same time. So let me show you why. Now, you're probably used to hearing that the olfactory bulb is what mediates smell. I think like everyone at this point knows that. But what's kind of interesting is that it turns out the lesser known nerve, the trigeminal nerve, also has a stake in this sensation. In fact, both of them contribute to smell, and they perceptually fuse to produce this multimodal sensation that we know. So let's take, for instance, something that we're all familiar with, right? When you take a whiff of vinegar, you smell sharpness. The olfactory bulb is reacting, but it's especially the trigeminal nerve that's going to give rise to that distinctive and recognizable sharp smell. And sensations invoked by these two systems are fused to be what we understand as smell. So it's kind of like how people might know flavor as being multimodal, smell is too. Now, these two systems also contribute to an interesting phenomenon. So if I hold like a flower to the left or right of my nose, its smell has little trigeminal stimulation. So my olfactory bulb might distinguish the direction of the flower's smell in stereo, but we don't actually perceive it consciously. So that's probably why people don't notice that the stereo smell in everyday life. However, if you use something that's like vinegar and you smell vinegar, you'll consciously be able to tell the direction or which nostril has a stronger sensation. And we're trying to take advantage of this kind of affordance that the trigeminal nerve allows, which is a conscious stereo smell. Now, we're taking that advantage of that the trigeminal nerve being able to feel left or right intensities to make a device that actually reproduces electrical stereo smell. And that's why the device is at the user's nasal septum, where it can already be accessed by the trigeminal nerve. It can already access the trigeminal nerve with its small form factor and without implantation or long prongs. Here we have two small boards that just go up the nose. It uses magnets to hold itself in place, and it has tiny electrodes and a small battery, and it fits inside the nose, which is pretty convenient. We then validated our device with two experiments. As the first exploration of electrical stereo smell, we found out that one, we can choose electrical waveforms that create stereo smell sensations, and we characterized this first for intensity. So we were able to vary like the level of like how strong the sensation is, and more importantly, direction. So we were able to show that by varying net charge, which is one of the things that we controlled for, you could actually change the direction going from left, this is on a Likert scale, to middle, 0, and then to right sensations. So the stereo smell is very evident across participants. These people were untrained, just reproduced the Likert scale and told to evaluate it. And from this, we actually produced 9 candidate waveforms to roughly encode direction and intensity. Now, using these waveforms, what's super cool, at least to me, is that using 4 participants that had never been in the first study, right? So they were never trained, they were never included in the generation of these 9 waveforms, could navigate a virtual odor field. AKA there's no smell, there's nothing in the room, they are only navigating using electrical stereo smell that is rendering a fluid simulation in the room. And what's interesting is that they're able to navigate this virtual odor field in what seems to be a similar manner to how they would search a trigeminally stimulating chemical odor in the room. So we compared this with a similar setup. So the CFD is actually modeled after a real setup where we have peppermint essential oil that is diffused into the room actively, and they are asked to track and find the source of the odor, both in the real context for the chemical smell, as well as the electrical stereo smell. And here you can see that the error from the target's pretty similar, as well as the time. Now, to conclude, we ended up exploring a new way of producing certain smell sensations, right? So this is not all of them, specifically trigeminal sensations via electrical stimulation, and showed that we could actually create noticeable stereo smell. Now, the main limitation is that we found out how to create that sense of direction and intensity, so we characterized for those two, but we didn't actually characterize for different trigeminal qualities or sensations like tingling, refreshing, sharp, warm. We were able to get these kinds of things anecdotally. That's something that we're interested in exploring in the future. However, what's kind of cool is that you could imagine, since it's not doing the full spectrum of like a smell sensation, you can imagine combining this with existing olfactory displays to have a wide range of different sensations. And especially what we're interested in is we kind of hope to investigate the system's potential use as an assistive technology for people with smell loss, aka people who, like people who have anosmia. I think that's a word that's become more popular or more known since COVID-19 hit. And these people often retain function of their trigeminal nerve. And so the idea is that you could imagine potentially mapping olfactory stimulation to trigeminal stimulation so that people who lost their sense of smell could actually notice gases in the air again, whether that's odors or other things. And you could also imagine doing things like changing what sensors pair with this device. So this is a stimulator that's going to be paired with any kind of like gas sensor or odor sensor system. So you could imagine even allowing people to perceive gases that we can't innately perceive, such as carbon monoxide. I think most people have carbon monoxide detectors in their houses. And that's because this is a dangerous compound that we can't natively smell. But even cheap gas sensors like in an Arduino kit can actually detect these at very low levels. So you could imagine allowing people to smell a wider range of gases in the air. Now, the reason why we're so excited about this is that it also extends our investigations on making trigeminal nerve an interface for computing technologies by kind of following up on our Kai 2020 chemical exploration of the trigeminal nerve. And I think I'm about at time at this point. So thanks for listening, and I'm happy to answer any questions. Yeah, I'll go ahead and, should I just leave it on this screen? I don't know, Brian?
That's probably fine, yeah.
Sounds good.
Yeah, let's thank Jazz for a great talk. So we have some questions. So Sophie from YouTube asks, does it feel like smell? Like, what are you smelling, or is it just like electricity in the nose?
So it doesn't feel like electricity in the nose. It does have sensations that are smell-like. As I mentioned in the talk, this is like the smell sensations that are more unique to the trigeminal nerve. So you can get things like stinging, warm, refreshing, wasabi-like feelings as well, smells vinegarish, and you can't get things like necessarily like the smell of like a pine cone, right? Because that requires also the olfactory bulb being involved. But the cool thing is that you do perceive this directionally. That's quite evident just in the feeling of it, and that's quite unique to the system in particular. So if you took the stimulator and put it on like across your finger pad, you wouldn't have like a stereo sensation. This is like really unique to the trigeminal nerve and the olfactory bulb.
So like if I did have another smell in the air, like say menthol or something like that, and then you added this stimulation on top of it, would it feel like I'm smelling menthol in a certain direction?
Yeah, so we didn't actually test for the combination of those two sensations. But that's something that we're interested in doing in the future, and hopefully it would is the idea. Probably one of the things that you have to take in consideration is that the relationship between the olfactory bulb and the trigeminal nerve is very odd. Sometimes trigeminal stimulation, if it's very, very strong, can actually detune your sensitivity to smell, or the inverse. So it could also alter your perception of the odor to some extent, which is a cool idea if anyone's interested in that. But yeah.
Cool. So it might be odor dependent. Okay.
Yeah.
Yeah. Okay. Jorge has a question. Do you want to ask it, or I can ask it if you want to unmute?
I can ask it. Thank you very much. It has been an incredible conference. I want to know how the smell signals are affected by the COVID-19 sickness.
Yeah, so I wouldn't be able to answer the exact way that it's modifying smell perception. There is something called the Global Consortium for Chemoreception Research, if I remember right, GCCR, if you're interested. And that's a bigger group of people that are curious about how it's modifying it and why in particular. But it does actually reduce it. And one of the bigger symptoms is smell loss, right? So people have been looking into doing things like smell tests, for example. There's also potential in the area of like decreased trigeminal sensation, but there are people that report long-term smell loss that kind of have what's called acquired anosmia, aka they'll suddenly not be able to smell at all in general. And this has like a bunch of side effects. Enjoyment of food is decreased. You might not be able to pick up that you're burning food in your house or that there's a gas leak at all, because gas leaks are dependent on something called an odor. They add something that's basically kind of like a sulfurous odor, like eggs. So if anyone loses their sense of smell, it becomes odorless gas once again. We're Captain. Thank you, Pedro. And yeah, I don't know if that answers your question directly. But in most cases, when it does affect the sense of smell, it's either going to be anosmia, which is complete loss, either short-term or long-term. There's a lot of cases that are coming up in long-term smell loss. And some people, when they're recovering, they have something called parosmia or hyposmia. Parosmia is like when you have distorted sense of smell. So everything might smell negative, or like vomit, for example, and you can't distinguish anything. Or you have hyposmia, which might be a very decreased sense of odor for a long time. Yeah.
John Byro from YouTube asks, apart from putting the PCB in our noses, is there any other setup required to make sure it shocks our nerves and not just the skin in my nose? So is it just putting it on the skin sufficient, or do you have to do something deeper, or what?
So this is part of a conversation with Pedro that I've had for a while. So Pedro, you can jump in for your thoughts on this as well. The trigeminal nerve is what innervates the skin in the nose, right, and the nasal cavity. So the distinguishment, it might be superficial in some sense. The important part is that we're targeting the intranasal trigeminal nerve endings. So these are the nerve endings in the nose that get processed differently than the nerve endings like on your forehead or in your mouth, right? So you're not necessarily going to get, from what I know, at least in the literature, stereo sensations by stimulating the eyes or the tongue, which also has nerve endings of the trigeminal nerve. And it's just skin sufficient. So again, it's really about targeting a specific site, right? The nasal cavities. You could hypothetically stimulate other areas, but it won't produce this kind of sensation. Yeah, there is another nerve that I'm reading up about that might exist in the nose, which is the intracranial nerve 0. But I don't know much about that, and it's contested as to whether it exists or not. So for the moment, I'd say that most of the innervation in our nose is the trigeminal nerve, and it's getting processed differently, which is the key point.
Anyone else have a question? If not, I have one last question. I really like how small this device is. Are there other devices of this kind of size? Because this is something I might even think about actually being okay with wearing, because it's just so small. It almost looks like a nose ring or jewelry or something like that. And I'm a programming languages researcher, so I wanted to have it point out code smells for me. Smelly code smells. But are there other devices of this size, or is that one of the key contributions of this?
So I don't want to say that we're the first, because I feel like one day someone's going to be like, surprise. But I'm pretty sure that we are, in the sense that, like, in terms of olfactory interfaces, they're all very bulky usually. However, there's Judith and Morris's work, which is quite small, but it requires like splitting the actuator from the full driving board. So like there'll be a small device, and then there'll be a reveal behind the ear where there's the full driving board. So it kind of splits these things. And then in terms of intranasal devices, I think this is the first time that there's like a fully wireless, untethered, like in the nose stimulation device. If anyone knows of any, please let me know. I think I've seen like Ken Nakagaki like mentioned a device that like is put inside the nose and that like creates light when air passes by, but it's not necessarily it's not like a interface system. It doesn't stimulate the smell. It doesn't stimulate trigeminal or olfactory things. So yeah, I would say yes. I'm just cautious because you never know.
Right. Sometimes you find something from 1980 and who knows what.
Yeah, exactly. I'd be hard pressed if the 1980s had this device, but yes. Oh.
All right.
Interesting. Do we have one more question?
Yeah, can we answer it in chat though? So we can.
Sounds good.
But let's thank Jess again, and then I think Andrew's up next. So Andrew Knut is going to be telling us about how to get some code reuse with your templates for building visualizations, so you can have lots of the flexibility of writing your templates, writing your visualization scripts by hand, but also the flexibility of a GUI as well. So Andrew, take it away and tell us about Ivy.
Thanks, Brian. Let me just get my things going. All right. Okay, hello. As Brian said, I'm Andrew McNutt, and today I'm going to be talking about mine and Ravi Chug's paper, Integrated Visualization Editing via Parameterized Declarative Templates. Now, every user interface design involves compromise, and the various available options in charting are no exception. Shelf builders like Tableau enable rapid exploration, but can make constructing specific chart forms difficult. Chart choosers, like in Excel, allow easy creation of specific chart forms, usually at the expense of flexibility. Textual programming, in contrast, via tools like Vega Lite or D3, can offer rich expression languages, but usually at the cost of an increase in exploration difficulty. In this work, we sought to understand how to combine the benefits of several common charting modalities while avoiding their deficits. To investigate this question, we built a prototype visual analytics system called Ivy. The root of the application looks a lot like the Vega Lite example gallery, and therein a chart chooser. However, if we click on any of these, we'll find something instantly usable. In particular, Ivy's editor configured to that chart form. One of the main ways to interact with this chart is via a familiar shelf builder style drag and drop GUI, where pills representing data columns can be dragged from the left into the shelves in the center column. The configuration of which generates a chart on the right, which in this case is a Vega Lite based waffle isotype. Now, unlike most shelf builders though, this GUI is generated by an end-user editable text representation, allowing for customization of the interface to taste and to task, customizations which can be saved and shared via Ivy's gallery. Each chart in Ivy is a parameterized declarative template. These templates are special functions which contain parameters or arguments and a function body, which, when combined, produce a visualization. The typed arguments to this special function describe what values can be used and what GUI elements will be generated to represent them. Here we see several parameters controlling features such as color and size. The template body consists of parameterized JSON-based visualization grammars, which currently can be Vega Lite, Vega, a unit visualization specification language called UnitVis, and a toy data table language. Ivy's language support is extensible, so additional grammars can be added as needed. Backing this parameterization is a formal language specification, which you can find out more about in the paper. But what it boils down to is standard JSON enhanced with variables and conditionals. Let's look at an example. Here's a template for a bar chart with parameters that are shown in their GUI representation. Variables are inserted into the text through string interpolation based on escape brackets. Here we see the connection between the GUI element called ydim and the corresponding place in the code. Next, let's see conditionals. Conditionals are simple control flow operators that, if they evaluate to true, are replaced by their true branch, and if they evaluate to false, are replaced with their false branch. That is, if there is one, or as here, the containing key, which here is sort, will be deleted. To make this actually do something, we give a specific values to the parameters by setting ydim to age and xdim to people, which are columns from the data set. The conditionals are evaluated and variable values are replaced as appropriate to generate this Vega Lite spec, which finally can be rendered, producing this chart. So just to briefly recap, templates are special functions that enable reusable charts by enriching JSON-based declarative visualization grammars with variables and conditionals. While variables and conditionals might not seem like a lot, they can do a surprising amount. To demonstrate this, we took all of the examples in the Vega Lite gallery and transformed them into templates. when we conducted this exercise, there were 166 unique examples, which we factored into 43 unique templates, yielding a 3.5x compression ratio, indicating that in addition to their other usability gains, templates can act as self-documentation for collections of charts and act to improve a grammar's learnability. We also conducted a similar exercise with Google Sheets Chart Chooser. This guy, which you might have seen in Google Sheets, it presents a set of 32 charts across a variety of functionalities, such as maps and pie charts and 3D pie charts, everything fun. We reproduced this collection of charts with 16 Ivy templates, yielding a 1.88x compression ratio, which again highlights the compaction available from this approach. To further test the expressivity of our approach, we also reproduced the shelf builder Polestar, which itself is a simplified version of Tableau that was created to evaluate the visualization recommendation system Voyager and also Voyager 2. We were able to successfully reproduce it as a single Ivy template. In addition to increasing our ability to concisely abstract over families of charts, this architecture also enables some useful features as sort of emergent properties of the architecture. The first, called fan-out, enables exploration within a template by allowing simultaneous viewing of multiple parameter configurations. For instance, say you'd made the scatter plot and you wanted to try out some different color variables. Rather than juxtaposing them in time and making your comparisons mentally, that is, setting variable to one thing and then another, we can simply fan out or fan across the color parameter by first selecting the fan out menu next to the parameter of interest, which is this little lightning bolt, and then selecting the values of interest for that parameter, which allows us to see a permutation of the chart for each selected value simultaneously. Once you found a configuration you're happy with, you can collapse back to a single chart by selecting the checkbox in the upper right-hand corner as desired, or modify all the charts at once, however you wish. The dual fan-out is our catalog search, where fan-out allows for variation within a template. This feature allows for variation between templates. It uses a simple type-based matching algorithm in order to recommend chart alternatives based on current data selection, here shown represented by several queries. The options that are available to this recommendation algorithm are user-created. The options that are available are user-created, which causes this feature to be something sort of like an extensible version of Tableau's Show Me. This allows users to explore templates by smoothly moving between them without having to start the data analysis process from the beginning every time they create a chart. This relatively simple matching system is able to capture much of the functionality from more sophisticated recommendation systems, again, such as Voyager 1 and 2. Now, one of the more exciting aspects, at least to me, of this approach is that it allows for opportunistic programming flows. In traditional programming contexts, opportunistic programming involves situations where the user finds something that they need online and they need to tweak it to their purposes, such as when you find something that almost does what you need on Stack Overflow and you need to modify it just a bit, or, well, maybe just a lot. So Ivy explicitly supports this workflow, at least in the language of JSON-based grammars. So say you found an example you like somewhere on like the Vague Light gallery. This can be great, but maybe a little bit difficult to actually get running for your data. With Ivy, you simply paste that grammar snippet into a new template. You are then provided with a series of automatically generated suggestions to transform that snippet into a reusable template, and you can, customize it however you wish. Then, when you're done, you can save and share your newly created template to the Ivy template gallery so that others can use it, make use of your templatizing, and it can appear in the catalog search recommendations. So, in this work, we examined the consequences of taking a meta-language approach to visual analytics, which offers a number of useful features. It's grammar agnostic, allowing for use of any JSON-based grammar as may be needed by the current task. Exposing an underlying text representation enables opportunistic programming flows wherein users can leverage examples found online. It's at least as good as many alternatives, as it can literally reproduce some of them. And we've argued that we get the affordances of each of the wrapped modalities while avoiding their shortcomings. Of course, this approach, like any approach, has some limitations. Its meta nature prevents contextual suggestions based on the knowledge of the underlying grammar. This sort of logic is a staple of modern smart visualization systems, such as Lyra 2, Data Illustrator, and co. However, we believe this is addressable through additional refinements to our grammar API. We ran an approachability study with 5 former MS CAP students who are now all employed as data analysts. They were all able to effectively use the system for a variety of exploration and chart specification tasks, and spoke positively about it in comparison with other visual analytics tools. Although several of them noted that there is a presence of a learning curve. And so I go into greater detail in the paper, and so I endorse you to go look at this rather than just hear where I gloss over it. But we believe that this learning curve is not intrinsic to this form of multimodality and can be addressed through additional design refinements. The system that we described combines chart choosing, shelf building, and textual programming. However, this is not the first work to combine multiple modalities in visualization or visual analytics. In future, we'd like to see systems that combine not just visualization modalities, but also analytic contexts, such as spreadsheets and notebooks, as well as techniques like programming by demonstration. We're optimistic that the multimodality and meta layer approach found in Ivy and the lessons learned therein will be a useful starting point for future work in this direction. Thanks for your time and attention. You can find out more about this work at the top link, and you can try out the system at the bottom link. I'll be happy to take any questions you might have.
All right, let's thank Andrew. Give him a round of applause. Yeah. What I really like about Ivy is it's got a lot of features, and it seems like it can do a lot. And I think it's sometimes hard to wrap your mind around, what is the system all doing? It's like you can recreate Polestar. It can recreate an entire another system, right? So just to help me and maybe some of the listeners wrap our minds around this. So what's another example of where you would use, say, Ivy instead of, say, like Tableau?
Well, it's kind of I would describe it as maybe a competitor with Tableau. Tableau obviously has a really refined sort of data analytics ecosystem. Like a lot of its value comes from the fact that you can connect Tableau to specific databases, whereas this is a research prototype. And so has a bit of a less refined story in that direction. So like it's totally a valid thing to use. I know in a recent WIS paper, we were using it to generate some of the figures that we put in there rather than go through Tableau. So it's just a slightly different approach to visual analytics.
Yeah, I guess the question was like, what makes it different, right? So like you said, you actually were using it for something, and so why did you choose your system then over?
Because of kind of two things. I was able to do data exploration kind of in both like a chart form forward approach. So like I knew that I wanted to like make a particular looking chart. And so I was able to dive directly into that, but also I was able to do some more exploration-y things. And in particular, it came up most directly because of some opportunistic type things that we encountered.
So it's very good for both the exploration part of data analytics, as well as I want to make a really nice chart that fits my specifications exactly.
Yeah.
Okay. Good. Excellent. Okay, Will Brackenberry, do you want to ask your question out loud, or otherwise I'll read it? Okay, I'll go ahead and read it.
Oh, so sorry, I finally got to unmute. I can actually say it. Sorry about that. Yeah, so obviously really, really interesting. Thanks for presenting this. Did you get a chance to investigate it all in your user study, kind of how users might have switched between different task contexts? Because really highlighted how like each of the different potential aspects of Ivy are really, really useful for their individual use cases. And did you get a chance to see in your user study like how people then flowed between those in the same tool?
Unfortunately, we didn't really look into sort of the kind of mixed modality or like kind of how much mixed users sort of moved in between things. It was sort of the context of the study was more just to verify that this wasn't, a sort of a deal breaker for users of, who had experience with similar systems. I think future work should consider sort of what the sort of user experience of using this mixed modality is and how different modalities integrate therein. And I think kind of the thing to sort of like push the work to sort of make that super smooth is to integrate more modalities. So like Tableau and Ivy both have a very bad story around how annotations work. like the way that you actually add, details and refine, like, this data point contains data about Brian. That works super poorly. And so I think integrating something kind of like Illustrator into this as well, and what's sometimes called a visual builder, might sort of be the glue to put all these pieces together. Admittedly, there are, of course, other modalities still to stir in, like I was saying, spreadsheets and notebooks, but there's places to go still with the integration of the modalities. And I think once that integration has occurred, I think we're going to be in a better place to ask sort of like what it's like to flow in between them.
Thanks so much.
Ivy will become a super viz builder. Does anyone else have any questions?
If no one else has questions, then I can quickly ask another one. Just would you be able to expand briefly on how you envision like notebook type visualization being a different sort of modality from the other ones?
So I think the way a lot of visual analytics systems work is there's sort of like this static interface where you're sort of like dropping like pills onto shelves. And that's really because Tableau has been so dominant in the visual analytics space. Like every visual analytics tool kind of copies this interface. You look at Power BI or anything like that. It's a very sort of, this is the way it's done. But I think, there's space to sort of integrate code back into that rather than like people are excited, or people like Tableau because it is a no-code solution. And sort of one of the values that's built into Ivy's position is that no-code is great, but low-code is also good sometimes, and so is full code. And so being able to transition in between those, is useful for different tasks. If you have something that you need to change, you should just be able to go change it. You shouldn't need to fight through an elaborate set of GUIs to do that kind of thing. So my kind of vision for how notebooks and spreadsheets might integrate into this is kind of just graphs, shrug. I'm still getting there. So I guess watch this space for a follow-up.
Will do. Thank you.
Yeah, thanks for the questions. And I do like on Ivy, you can just copy and paste something you found online. I found this Vegalite thing online, copy paste it into Ivy, and it works. And then you can slowly template it as needed with some assistance. Yeah. So Yuji Tao has a question in the chat. Very interesting work. Wondering if you think of building interfaces that dynamically change based on the usage, would this reduce the learning curve or the number yeah.
That's a really cool idea. Sort of like an adaptive interface, like adaptive interfaces. Yeah, I think that's great. I think the biggest sort of hurdle that users found with the learning curve was sort of just getting used to the grammars. Again, no code is great, and so is low code. But like, if you don't know the code that you're stepping into, then it can kind of be a little bit of a stumbling block. And so the reason why we focused on CAP students is because these are students who I'd had in the visualization class I had taught. And so I was somewhat confident that they knew a upstream dependent of Vegalite called Altair, which is a Python-based wrapper for Vegalite. And so the transition into that grammar was hopefully, my hope was that it'd be a little smoother. But that seemed like kind of like the crux of the learning curve. And so I think maybe like something like structure editors that allow you to make smart moves across the code manipulation space, and sort of declare what you want to have happen to the code, and not necessarily like worry about learning a whole new language. But I also do really like this idea of adaptive visual analytics interfaces. I think the interface should be where you want it when you want it, and shouldn't get in your way. So adaptation seems like a great idea.
I like how you mentioned structure editors, especially for a grammar like Vega, which is it's a very particular grammar, but JSON doesn't give you any of those constraints that the actual grammar has, and so the structure editor could really help you out. Yeah.
I totally agree.
So let's thank Andrew again, and then next up is Alec Mazurski telling us about Magnet.io, passive yet interactive soft haptic patches anywhere. So we're going to learn about these very low cost to manufacture magnetic patches, so we can touch a lot of different things.
Hi, thank you so much for that introduction. Yeah, so hi, I'm Alex Mazurski from the University of Chicago, of course. And today I'm excited to be talking to you about our work on a new type of haptic actuator to add tactile output to everyday objects. This work was done.
Just before you start, do you want to reshare your screen without that optimization? Because we cannot really read much.
Oh, my apologies. Let me see here.
I think it's going to help with the readability.
Thank you for catching that. Let's see.
Maybe not. Depends on the internet.
We'll do our best.
Maybe slightly better. Not sure. Go for it. Sorry for the interruption.
It's a freeze frame right now, at least, but we'll see. Okay. Anyway, this work was done in collaboration with my colleagues, Shan-Yuan Teng, Romain Nith, and our advisor, Pedro Lopez. And what you can see here on your screen is our new haptic actuator, and it currently is vibrating against a user's finger pad. And when we move the finger away, we can see that the vibrating element is in fact a magnet, and it's being excited by an electromagnetic coil that's worn on the user's fingernail. You can see it vibrating there. And this isn't unlike classic vibration devices, aka linear resonant actuators that we have in our phones, since we too are using the typical components of coil, magnet, and spring. However, the difference here is that we have decoupled the active component, the coil, from the passive components, the magnet and spring. And we don't use any wired tethers, electronics, or batteries within the patches themselves. And so therefore, the big benefit of this decoupling is that we need only one power source to actuate any number of these passive patches. And so thus we can place patches on a wide range of objects in order to augment them with input, but more importantly, haptic output. Let me explain why we engineered the system, which is largely motivated by the fact that touch input has become ubiquitous in our environment, yet haptic output has not. As you can see from this collage of recent research, interactive devices now instrument all kinds of surfaces, giving functionality to walls, tables, everyday objects, as well as on the body of users. And to enable these interactions, tons of research has been done on sensors and sensing techniques, from computer vision to acoustics to tactile skins and more. And importantly, some of these sensing techniques can even be done passively, meaning they don't require instrumenting the object with electronics. Let us consider this kitchen scene from Synthetic Sensors by Gerard Lapout and colleagues as a thought experiment, as it depicts the general trend that we've observed in contemporary sensing technologies. Here they've added sensors so that the user can interact with all of the labeled points, A, B, C, and so forth, and these interactions get detected digitally. This effectively provides the user with ubiquitous input. However, consider what would happen if we wanted to add haptic output to each of these interactions in order to give meaningful eyes-free feedback. How might we go about that? Well, one option is to add haptic devices to each of the surfaces the user interacts with. For instance, I can put one on the faucet, then the soap dispenser, et cetera, until all the surfaces have been covered. And this seems like a reasonable approach, except it turns out to be quite difficult because in order to deploy a large number of actuators, such as linear resonant actuators or LRAs like I show here, each actuator requires a controller and communications, be it wireless or tethered, and more importantly, power in the form of a battery per actuator or tethering to a main line. And the key issue here is that this isn't just a few milliamps of current, like in the case of sensing. It's enough power to drive mechanical motion that's strong enough to produce feelable sensations, which we refer to as haptics. And so our technical open challenge is to perform haptic actuation at scale. And so here's our approach to actuation, which I previewed at the start, but let's revisit it in detail. We instrument the user's finger with one single wearable power source. This has a battery, wireless unit, IMU with magnetometer, microcontroller, and most importantly, an electromagnetic coil. Then we instrument any surface of the user's environment with many passive haptic patches, like this one that you see laying flat on the table. These are simply made from stretchable silicone with a sticky underside, making them easy to attach to objects. Again, the reason that I call these haptic patches is that the center magnet can vibrate when it gets excited by the electromagnetic coil. Importantly, the user is feeling this movement directly on their finger pad, despite us not instrumenting the finger pad itself. This leaves the user free to interact with their surroundings in addition to our haptic patches, which is an important theme of this work, as well as Touch&Fold, which was shown earlier today. And to fully realize this as an interactive patch, we need not only to actuate it to create feelable vibrations, but also to sense with which patch the user is touching. And so this allows the patches to serve as things like push buttons and other simple ubiquitous sensing interfaces. And so to do that, we implemented a simple sensing mechanism that is also passive and works via magnetism. So as the user moves to touch the patch, this nail-worn magnetometer shown there reads the patch's unique 3D magnetic signature that's produced by the 4 magnets at the patch's perimeter highlighted there, and that's how it's able to identify the patch. Let me use an application of ubiquitous haptics to further illustrate how Magnet.io works. Here we can see a user in their home using Magnet.io to control their environment. The user wears our coil on their nail, and as they walk inside, they tap the patch on their door and are met with a vibration, confirming in an eyes-free way that their home alarm is now disabled, so they're free to enter. Next, the user walks over to a patch on their wall that controls their thermostat, and as the user slides their finger to adjust the temperature, Magnet.io senses, using its magnetometer, which patch the user is touching, and then according to what they touch, they receive that haptic feedback to indicate their selection. Here's how Magnet.io contributes to how we think about haptics at scale. We liken our approach to that of the LRA, or linear resonant actuator, which is what's used in most commercial mobile devices, in that it's comprised of a magnet attached to a spring and a coil for exciting it. However, our design takes a sharp conceptual turn from that of the LRA, since we purposely decouple the magnet spring from the coil. And so this allows us to scale up the output by placing many spring magnet pairs everywhere, which are only activated when the user's wearable coil contacts them. And the advantage of this design is that we only require one coil, meaning it also only requires one driver circuit, one communication module, and one battery. So we can place these patches all over without any concern for that. Let's look closer at the patch in order to see how it embodies the mechanics of an LRA, aka that spring and moving mass. So to allow the mass to vibrate at perceivable amplitudes, we designed this spring mechanism as a long, slender silicone beam, as well as a cutout surrounding the center magnet so that the magnet can vibrate. And then additionally, we include this thin air gap in the design that allows the magnet to vibrate up and down even when the user compresses the patch with their finger, since their finger is mostly supported by the silicone surrounding it. And in contrast to rigid actuators like LRAs, our patches are soft and flexible because they're made mostly from silicone, and so this enables placing them onto a variety of surfaces with ease. We can easily detach and reattach patches to new objects in order to give tactile functionality, such as on the band of a smartwatch for controlling it, or a smart bottle to remind you to drink water when you pick it up. This conformability is not afforded by typical LRAs. In fact, Magnet.io patches are even weatherproof. For instance, a user may wash their smart kettle that's been instrumented with a patch because the patch itself doesn't contain any electronics. And so here's how we implemented our system, beginning with the haptic patches. So here's our fabrication process that we use to make the patches, which are made again of 2 parts. There's this soft and stretchable magnet that's made of silicone that's been mixed with permanent magnetic powder. And then that gets adhered to the second part, which is a flexible silicone mechanism that enables the vibration. And so first, we fabricate the soft magnets by mixing the silicone and magnetic powder, which is shown there. And then that mixture is cast into a 3D printed mold in order to shape the magnet. And then that mold is held between 2 strong permanent magnets that produces about a 1.1 Tesla field, which is quite strong, and thereby magnetizes and polarizes the particles, and those polarities align. And so this process results in a composite that has a strong permanent magnetic field while remaining flexible due to the silicone that holds it together. And so next, the rest of the patch, which embodies our spring mechanism, is just cast using pure silicone into a 3D printed mold. And then we assemble the entire patch by adhering the magnets to the mechanism with glue. And then for the implementation of our fingernail worn device, our coil has been designed in order to provide strong magnetic forces while maintaining this kind of compact, lightweight footprint that importantly doesn't occlude the user's finger pad, which allows the user to still feel their surroundings. We also designed this magnetic core that helps concentrate the magnetic field toward the user's finger pad in order to improve the device's overall efficiency. And the final coil design has 42 windings and weighs just 2 grams. The entire device, not including battery, weighs 4 grams. And the entire nail-worn device has our coil, custom PCBs that are centered around the NRF 52811 for processing the sensing and actuation, as well as providing Bluetooth communication. And our board features a motor driver that can generate 5 amps, but typically only 1 amp is needed in order to give subtle sensation. And small batteries, say on the order of like 40 to 150 milliamp hours, can provide about 100 to 300 haptic pulses. So we evaluated the technical performance of the device, both in terms of the sensing and actuation capabilities. While our main focus is, of course, on the actuation here, in order to enable that full loop interactivity, we included sensing by embedding these ID magnets in order to manipulate each patch's 3D magnetic signature. So we do that by varying the orientation of these surrounding magnets. And so this allows the coil to identify each patch from a set of pre-trained signatures by using its magnetometer like so. And in our experiments, we found this to give 99% accuracy for identifying 8 unique patches via a very simple rule-based classifier. We think that more sophisticated methods like a statistical classifier might allow this to scale further to a greater number of patches. And we acknowledge that there, of course, are many ways in which sensing may be implemented, such as RFID and many more. But here our intent is to rely solely on the magnetic properties. We also set out to characterize the vibration performance of the device. So to do that, we measured the vibration intensity generated when we placed a piezoelectric sensor below each patch and then held the coil stationary above the patch at about 6 millimeters distance away and excited the coil with square waves. And in order to see what the frequency response looked like, we repeated sweeping across each frequency and looking at the intensity generated. And our design goal here was to maximize the vibration that was felt at around 250 hertz, where the human finger pad is most sensitive to these kinds of vibrations. And so we varied design parameters in order to determine how the geometry affects the vibration characteristics. And the first one that we studied was the effect of the spring width, which we expected to influence the resonant frequency and amplitude. And we varied that for 4 different spring widths. And we can see here a spring width of 1 millimeter resulted in a resonant frequency at about 100 hertz, whereas 2 millimeters resulted at 300 hertz. And so we moved forward with the one that was closest to 100 hertz so that we could then decrease the mass that we attach in order to increase the frequency. If we want to talk more about vibrational theory, talk to me offline. And so from here, we found using then a magnet diameter of 7.5 millimeters was able to give us a peak close to, close to that 250 hertz goal. And so we used that for subsequent studies. And finally, we compared the performance of this sample to that of an LRA and found it to produce similar magnitudes to an LRA driven at 4 volts. Let me show you a couple scenarios in which we're currently testing Magnet I/O. We believe this design is useful for eyes-free interactions, such as controlling the looper on a guitar. And additionally, since our interactive patches are made of silicone, the patches can be shaped to their application as well as drawn on, like here, where a user has added a patch to their favorite toy in order to feel its heartbeat when they pick it up. So to summarize, we introduced, designed, and evaluated a one-to-many actuator to allow haptic interactions to more easily scale. We tend to think of Magnet I/O not necessarily as an end product, but as a hardware and fabrication idea that may inspire more ubiquitous use cases for haptics. For more details, please check out our paper, or even better, feel free to reach out to us directly. Thank you for tuning into our talk, and thank you to all involved in organizing this. It's been really inspiring hearing about everyone's research. Thanks.
All right, let's thank Alex. Thank you for the fun talk. Okay, I don't see any questions in the chat yet, but if anyone wants to pipe up with a question, you can go ahead now. Oh, here we go. Ken has a question. Do you want to ask it out loud, Ken?
Yeah. Yeah. Great work. Congratulations. I was wondering if you have thought, of like other like utilizing this architecture for other like surfaces that already has like magnetic or ferromagnetic properties. I'm sure there'll be like lots of technical difficulties, but there are already like magnetic surface we have in everyday life, and without really adding patch, we could also like adding, I don't know, like haptic textures on top of it, these surfaces. So yeah, just wanted to hear your thought about that.
Definitely. And yeah, we've talked a little bit about how this might be used to add textures on top of surfaces. And it gets into some interesting ideas of like where the vibration is really being felt or where it's happening. And so here the vibration is happening mostly at the patch, but I think it would be interesting if the patch were restricted from vibrating. It might be felt more at the coil on the back of the nail, which is a little less desirable. So I think, at least in this case, we've thought about it mostly in terms of like allowing the patch itself to vibrate. If we make like a continuous surface that could vibrate, it would be a little bit difficult because of its mass. But I think if we made it thin enough, we could render textures like that.
Yeah.
Yeah,
it's cool, because also like your finger may also like stick to the surface, so you start to feel, I don't know, the surface is more stickier or something. I don't know, but there's really cool. And
once you get into film stuff, it
coil.
gets a little weird. That's right.
Yeah, cool.
Thank you, Ken.
Thank you.
We have a question on YouTube. Richard Lee asks, very cool, love the concept. How is the device attached to the finger?
So the device is attached to the finger using a type of really sticky silicone produced by Smooth-On called Skin Tight. It's typically used for like doing, what would you call that? I guess like prosthetic makeup design, I guess. So like makeup artists use it for things like showing like wounds and things like that, but it's super sticky and skin safe, so it can just stick right onto the body very easily. And so that's how we're sticking it just directly on. Yeah. Yeah, basically tape.
All right, I'll pipe up with a question. So in the very beginning, you showed an image of you slapping these on your coffee mug, right?
Sure.
What kind of feedback do I want to get while I'm holding my coffee mug in the morning?
Yeah, that's a good question, and something we've experimented with a little bit. There's certain things where like maybe if you pick up your device, it happens to remind you like, oh, maybe you should drink water right now, or with a coffee mug, maybe it could give some indication of temperature without you actually reaching out and grasping it. If it's too hot on the boundary, you could just feel the vibration prior to touching it, so some kind of affordance right there. Something along those lines, yeah.
All right, thanks. Anyone else want to pipe up with a question? All right, I'll ask one more question. You talked at the in your video, as well as you mentioned at the end here, that there are some fabrication techniques that might be more broadly applicable. What do you consider, out of the things that you did to make these patches, what was the most unique thing that you tried that you think other people should think about using?
Yeah, so these kinds of like soft magnetic materials have been quite popular in like the soft robotics community for doing things like making little quote unquote robots that swim and do locomotion and things like that. But I think there's a lot of other applications that can be explored in terms of like interaction, such as maybe shape changing materials that can bend and fold based on how you tune the magnetic properties of the patch. So here we just showed if we magnetize it in one direction, you can get one plane of motion out. But I think that there's more degrees of freedom to be explored in there down the line.
I was just wondering earlier today, and this talk again brings it up. Like, could you make a simulated muscle by, you have one layer of some magnets, another layer with some magnets, and so on and so forth, and then You turn certain electromagnets on and off and make a simulated muscle fiber or something, or muscle or something.
Probably. There's all kinds of ways of going about creating like force feedback devices or artificial muscles. Magnets are just one way of going about it, but yeah, probably.
Any final questions for Alex? Okay, if not, let's thank Alex and his collaborators again. Thank you for the great talk. All right, this is it. The last talk of Kai Chicago 2021. We have Valerie Zhao going to present on understanding trigger action programs through novel visualizations of program differences. So helping people understand these trigger action programs through different ways of describing what they do in different scenarios. And this paper won an honorable mention, so congratulations to Valerie and the collaborators. Valerie, take it away.
All right, thank you, Brian. Just give me a second to settle in. Okay, so hi everyone. I'm Valerie. I am a third-year PhD student working with Blaise at the University of Chicago. And in this talk, I will present our work developing new ways to identify and visualize differences between trigger action programs for end users. So trigger action programming, or TAP for short, is an end user programming paradigm commonly used to automate web services or smart home devices. It is currently supported by multiple platforms such as IFT and Mozilla's WebThings. In TAP, each program contains one or more event-driven rules, and each rule follows the format of if some event happens, then do something, such as if Alice falls asleep, then lock the front door. We can also specify conditions to restrict when the rule executes. If Alice falls asleep while it is nighttime, then lock the front door. So let's try to program something with TAP. Here's something Alice might want. She might want the front door to be locked when she's asleep or when it is nighttime. She might also want the security camera next to the door to be on whenever the front door is unlocked. So a trigger action program that satisfies both of these two goals would contain 6 rules, which can be a lot to keep track of, especially for non-technical end users who are the target users that TAP was designed for. So TAP might seem easy, but in general, when there are many rules in a program, it is hard to figure out how the rules depend on each other and what will actually happen. This is a problem when the user is trying to compare trigger action programs. You might ask, why would they want to compare trigger action programs? 1, when modifying or debugging a program, the user might want to compare the older and newer versions to see whether their modification was successful. 2, when merging existing programs to the current program that they're writing, like reusing code, the user might want to check for exactly what behaviors have been introduced. 3, users might take advantage of existing automated tools, which can generate candidate trigger action programs based on some input or specification of what the user might want. In this case, the user might want to compare these candidate programs and find one they like. To help with these scenarios, our work introduces new ways to help end users understand differences between 2 trigger action programs, especially when the 2 programs are highly similar, as one might expect for the scenarios I described just now. I'll present the interfaces using this running example, and you do not have to read these programs in detail. One form of difference between programs number 1 and number 2 is the text. The 3rd and 4th rules are different here. This is the kind of differences that many conventional software diff interfaces would focus on. So we designed a text diff interface for TAP as well. As you might notice, we modeled this interface based on the one on GitHub. It shows the 2 programs side by side, with the red and green colors indicating rules that differ between the 2 programs. But with this interface, the user is still left with the work of figuring out what's going on in the system. Therefore, we propose, implement, and evaluate 2 new ways of displaying differences between related trigger action programs beyond just the text. Back to this running example.
What is true about this pair of programs is that if Alice was asleep during the day with the door locked and someone tries to unlock the door, program number 2 will leave the door locked, while program number 1 will have it unlocked. This is a situation in which program number 1 results in a different outcome than program number 2, so we will call this an outcome difference. We first designed a flowchart interface showing outcome differences. Each flowchart sets up a situation. The flowchart starts by showing the initial state of the smart home system. In this example, the flowchart shows that the situation starts off with Alice asleep during the day while the front door is locked. Next, the flowchart shows an event that happens. In this case, someone tries to unlock the door. On the right, the flowchart forks to show that the two programs achieve different outcomes. On the top branch, we see that program number 1 results in the door being unlocked in the end, while program number 2 on the bottom has the door locked. And that is how this interface communicates outcome differences. However, maybe Alice already knows that she wants the door locked in the end and doesn't care to know what the other possible outcomes are. In fact, if there are many programs under comparison, Alice might have to sort through all those comparisons and the many possible outcomes that might be irrelevant to her goal. Therefore, we designed an alternative interface that asks the user which outcomes they want in specific situations. Each question asks about a situation. We first show the part of the flowchart that sets up the situation. Like the example before, this situation starts off with Alice asleep during the day and someone trying to unlock the door. Below that, we present the possible outcomes achieved by the set of programs under comparison. The user can select one or multiple of these outcomes that are acceptable to them, or specify that none of the outcomes are acceptable. Let's say Alice chooses to have the door locked in this situation. Based on the user's responses to all the situations, the interface shows how well each program matches the selected outcomes. Given Alice's choice for the situation we just saw, and maybe similar choices for a few other situations, the interface shows that program number 2 is most suitable for what she wants, while program number 1 is not. So those are two ways that we can communicate outcome differences. But it's also possible that instead of outcome differences, Alice might want to look at differences in the general properties of those programs, or these two programs. Our program number 2 has the property that the door is always locked when Alice is asleep, but program number 1 does not have this property. We designed a property diff interface that highlights these differences. The design of it looks a lot like TextDiff and is inspiration from GitHub, but it lists the properties instead of rules for each program. Here we see that program number 2 does have the property I mentioned before, while program number 1 does not. The types of properties we support are based on prior work and are mostly statements about what will always or never happen in the home. In addition to designing interfaces that display differences in outcomes and properties, we also introduced algorithms for efficiently identifying these differences. We model trigger action programs and the overall home as transition systems. Each node in the transition system represents a possible state of the smart home. In this simple example of a transition system, the only variables we care about are whether Alice is asleep and whether the door is locked. That gives us 4 nodes or 4 possible states of the home. Any changes that occur to the home or its environment or its occupants transitions the system from one state to another. Examples include the weather changing, Alice falling asleep, or someone unlocking the door. We use directed edges to represent transitions here. The rules, which are highlighted in orange here, redirect transitions from the original destination state to a new destination state. Here is another rule, redirecting another transition. And what can happen is that with these rules redirecting transitions, it renders a system state unreachable. So like this. with these two rules, the door will never be unlocked while Alice is asleep. In general, our algorithm looks for the differences in the transitions and in the unreachable states to determine differences in outcomes and properties. Please see our paper for more details. I will now talk about how well our work helps users reason about tap differences. Our user study was conducted on Prolific, which is an online participant recruitment platform. 107 participants' responses met the quality threshold to be included in our data analysis. Participants were randomly assigned to one of the 4 interfaces I described before, or a 5th interface that showed just the programs themselves. We asked participants to complete 6 tasks comparing related trigger action programs. The tasks were presented in a randomized order. Tasks number 1 and number 2 required comparisons between a few simple programs. The other tasks involved complex programs or involved many programs. Most participants completed the simple tasks correctly regardless of the interface they used. But for most of the complex tasks, our novel interfaces that show differences in outcomes and properties significantly outperformed the traditional interfaces that show differences in text or the programs themselves. A more comprehensive report of our findings can be found in our paper. Based on these results, we believe our interfaces, which rethink how we communicate differences between related trigger action programs, can help non-technical users better reason about automation systems. Thank you for your attention, and I'd be happy to take questions.
Thank you, Valerie. All right, does anyone want to throw out any questions there? I don't see any in the chat yet, but you can unmute and ask if you'd like. I have a quick question. Maybe I wasn't paying close attention. You said there's for the outcome differences, there are two treatments. One was this flowchart, and the other one was question answering.
Right.
What was the difference between them? Like in the question answering, were they asking their own questions, or was it just?
So in the questions one, the interface asks the user questions about what outcomes the user wants.
Okay.
And then based on the user's response, it tells you what programs are most suitable for your needs.
Okay. All right. I have a follow-up question. So so the system does some, looks at the state graph, looks for differences in the state graph, in the state transition graph, and then it shows those differences in some prioritized fashion, right? So in the examples you have here, on the one example on the right, the thing you're showing first is that the front door lock will always be locked. And then, so how does it choose which one to show first? Is there a ranking algorithm that we think that this is the most important difference between the program, or is it just random?
So currently the system does not do that. The order here is it's essentially we just show the properties that both programs share first, and then the rest are the properties that is in one program but not another. That is a logical extension. If we could ask more questions to the user about which devices or which states you care more about, then we might be able to incorporate that.
I have a question in that space, Brian, if I can jump in there. Yeah. Valerie, I like that idea. Are you saying that sort of like user in the loop, then it would come back to the user and kind of like, hey, rank these 3 things? Or is that something like that? Because I could imagine that being really beneficial.
Mm-hmm. Yeah, it could be. I think there is related work on that. Like, I guess the second author, Lefan, has a trace-based paper where essentially you look at the traces in the smart home and then present information or programs that could be synthesized based on those traces. And I believe the user is able to rank the rules for that system and to determine like what is the best rule or best program.
Mm-hmm. Yeah, I think there's still something really interesting about using your diff and then ask user to refine somehow a little bit. That's really cool.
Mm-hmm.
Thank you.
Anyone else want to pipe up with a question? Okay, so another question I had is, so you can have in your state graph, you can have, states that are never reached. Does it tell you about rules that could never fire because they require you being in a state that you can never reach?
So yeah, I guess this system would not tell you that, but theoretically you could analyze the graph and yeah, you could identify that information.
All right, I'll ask one more question, then I'll open it up one final time. What's the size of the state space of the programs that you were analyzing, right? So in the example that you showed, you had two things, each in a Boolean state, so you had state space was like size 4. There are 4 different possible states altogether. Mm-hmm. So for your user study, what was the state space size of these programs?
Right. For the user study, it depends. So for the last task, which had the biggest state, biggest transition system, I think it had 2 to the 7. All right. There were 7 variables, and each variable was binary. So they had quite a few states there, and for that, my machine was still able to generate the differences in a matter of a few seconds. So typically, yeah, it is an exponential growth in terms of the transition systems. But maybe something I should have mentioned is that, when the user is trying to compare 2 programs, it doesn't necessarily have to be all the rules that apply to the smart home. It could be just a subset that applies to the task they care about. Like it could just be the subset that applies to the lock. And so that actually does reduce the number of states we need to model.
Yeah, that's a good observation. Thanks. Anyone else have a question?
Yeah. I have an opportunistic programming question. Say Brian's house is IoT, and my house is also IoT, and Brian has some really cool setup that like a rule configuration that he's told me about, but he probably has different devices, probably passive magneto things, and all the fancy futuristic technology we've been considering here, and I've tried to emulate his setup. Is there anything that how could these program difference visualizations help me sort of debug my way through like kind of adapting the rules Brian's told me about, or like that be a serious extension, or sort of like how would opportunistic programming work in this context?
So in the case you described where like you're trying to adapt Brian's rules, I think there is definitely opportunity here where you can simply, I think I mentioned before that like in the case of like code reuse, when you're trying to merge existing programs to your current program, that you can see like, oh, what's this new program compared to my existing one, even if it's empty. There are these new behaviors that have been introduced into my system. So I would say that is an application, definitely. It is possible that your home has a different set of devices than Brian's home, And in which case we can still compare the two programs. We will just take a union of all the devices that you guys have.
Interesting. That makes sense. Thank you.
All right, let's thank Valerie again, and let's also take this opportunity to thank all of our speakers in this session. If you have any further questions, you can drop them in the chat, but I'm going to turn it over to Pedro to deliver some concluding remarks.
Yeah, I have just a few notes for all of you, but mostly it's just thank yous. So thanks everyone, that made it possible. Thanks all the speakers from these 3 sessions. I think it was a lot of fun to kind of see, the UChicago Computer Science Department presence at the different conferences. I hope we do this not just for Kai, but maybe for more conferences that we submit a lot to. So thanks everyone, and I just wanted to say also thanks for the 3 moderators. Thanks Jasmine, Brennan, and Brian. They did an incredible job and made the sessions so easy to interact with and so much fun. Thanks everyone for organizing, especially Tom Dobes, who's like making sure that this all works on Zoom, on YouTube, and Rob Mitchum, who makes sure that people know about this and they could register on time and everything. We're really hoping that at Kai 2020, we're probably going to see you in person. But if not, we'll do another one of these because it's a lot of fun. But also I wanted to just say to the students at UChicago that might be listening to this over YouTube or here, if you're interested to know more about human-computer interaction research at UChicago, we highly recommend you just subscribe to the UChicago. It's a mailing list, but it's also this webpage where you can see new things that are going to happen. Sometimes we do talks, sometimes we do all sorts of things. So I can highly recommend Katya's. She's an assistant professor at UC Davis, and Patricia's talk as well. She's a postdoc at the University of Washington. She can talk about HRI. Katya is going to talk about her crazy research at the intersection of HCI and fashion. And these are just some fun things we sometimes do to talk about HCI among faculty, students, and everything. So highly recommend subscribing to the HCI Club. And that's it. Hope next time we meet is at this beautiful building at the campus of UChicago. Thanks everyone for coming. And bye.